planning to start 8:30. We have the streaming waiting, so we will go for the event from now. Yeah? Yeah. Hello? Yeah, it's echo. Hola. Hola, hola. Pero dice que hay eco. Ah, ya está. Vale. Okay.
Good morning and welcome to AIMPLAS. It's an honor to AIMPLAS to host the ASADAMES Screen Printing Forever event. I want to thank ASADA to give us the opportunity to organize and to celebrate this international and relevant event in our facilities. I want to thank also the participation of the speakers that have traveled from different European countries, and also to all of the attendees, especially due to the COVID situation. For that reason, we have considered all COVID prevention measurements to offer to you a safety event. I want to introduce who is AIMPLAS. AIMPLAS is the Plastic Technological Center with more than, it's a lot of echo. AIMPLAS is a technological center with more than 30 years experience in the plastic sector. Our team is made up of more than 200 highly qualified professionals, about 60% of women and 38% of men. More than 10,500 square meters of facilities divided on pilot plants and laboratories that we will have the opportunity to visit at the end of this workshop. We are market-oriented, and we are involved in those industrial sectors in which plastic materials is a key material to develop these products. For us, it's quite important food safety and advanced technologies for preservation and packaging. Also, we are involved in projects, in research projects regarding energy, construction, transport and mobility, and also regarding electronic, in different research and developments for protection against electromagnetic interference and electrostatic discharge, flame retardants, and also regarding plastronic, to develop new conductive plastic materials, flexible printed electronics, and in-mold electronics. We are also involved in agriculture and livestock developments, sport and leisure, medical application, aquatic environment, and preservation of cultural heritage. We cover the whole value chain in plastic, from polymer synthesis, raw material development, compounding, manufacturing processes, to develop a market-oriented application, and we also cover the end of life of these products, recovering of plastic waste. Our main technologies are agriculture and aquatic environment, construction and renewable energy, decarbonization, engineering, sustainable and future mobility, packaging, mechanical recycling, chemical recycling, health, and chemical technology. Our laboratories involve characterization activities. Also, we have a laboratory addressed just for automotive and transportation industry, food contact and packaging, biodegradability and compostability, and tenders and standardization. We are focused in different technology readiness level, from 3, 4, 5 regarding research and development, till a product quite close to the market. Our research areas are based on key-enabled technologies such as nanotechnology, biotechnology, advanced materials, sustainable development, industry and the future, and plastic products development. And our aim is to focus to overcome and to develop technology focusing societal challenges such as health, Industry 4.0, circular economy, climate change, food safety, sustainable agriculture, and sustainable mobility. We have also different technical services, such as analysis and testing, processing and prototyping, technical assistance, and competitive intelligence and technology watch. We provide value through results for different activities regarding characterization of polymers, additive and fillers, and residual substances, mechanical properties, optical properties, rheological, physical, and performance against external agents and VOx emission. In fact, AIMPLAS laboratories have earned the most accreditation for plastic accordance to ENAC accreditation for plastic SASH. These are our 4 industrial laboratory sectors: packaging, construction, automotive, and biodegradation. And also for AIMPLAS is quite important the training activities for the different industrial sectors. For that reason, we develop tailor-made training for companies, face-to-face training, online course, AIMPLAS certification, expert in plastic, and we have official training, an official master degree with University Politécnica of Valencia. And finally, just to say that we organize key conferences and seminars for the plastic industry. Ones of that are national, but other ones are international activities, such as Plastics Are Future or International Biotechnology Seminar. That's all for my part. I hope you will enjoy this workshop and you will enjoy the Valencia city. Thank you very much.
Sorry, we have been experiencing some problem with the echo. Maybe we could switch off the speakers, because in the room we don't have much problem to project our voices. and the microphones can collect our signal for the streaming.
Hi, good morning, everyone. So, yeah,
Switch off the loudspeaker here in
the
room.
Okay.
Because there's a lot of
It's an echo.
in it. Yeah. As far as we have the signal from microphones, we don't need a microphone for broadcasting. Well, we don't need the loudspeakers.
So I switch off this one, maybe?
No,
No.
lo tenemos que dejar encendido para que se
Well, carry on.
mande la señal.
Yeah. So good morning, everyone, and thanks. And as my colleague Susanna said, thank you very much to join us either in person or either digitally. We are delighted to participate in this event and to be here at this table, joining Susana Otero from AIMPLAS and Pedro, and perhaps I think Mr. Asada Hideaki is going to be online.
Well,
unfortunately,
I
no.
will have to recommend
So,
that
join.
for some health problems, he will not be able to join us.
So join Pedro. We have been supporting this event for many years now, and we hope to continue this collaboration in the future, and also to support the participation of our members. Well, my name is Susana Baraswain, and I represent the Functional Print Cluster and the technological platform 3Neo, an innovative and transversal cluster which brings together 98 companies, technology and knowledge centers in developments that can be carried out using these technologies to the business industry, to the market, and to promote technology transfer, dissemination, demonstration, and internationalization activities. We represent a technology since 2013, and we can say that it's a value chain that has been transformed for the years. We came from a really traditional technology, and now we represent a really high innovative product with multiple applications, low cost, and lower environmental impact, and that is our strength. We have moved from a traditional sector to an innovative and transversal sector that can transform all application markets and industry, as Susanna said, mobility, automotion, packaging, electronic devices, health, wellness, construction, and habitat, energy, and logistics. You can see here our value chain. We have been working on these value chains for the last 4 years, and we insist always in the market. Working on the market, we can work in the rest of the project, and we can join the rest of the members of the value chain. And this is our paperwork at the moment. Those are our working areas. As you can see, the electronics, the biofunctional printing, packaging, and all the additive manufacturing, 2D, 3D, and electronic 3D. And regarding international, we are working in an international strategy that we want to join different members participating also in European projects. At the moment, we are leading a COSME-GO International, joining with other 4 clusters from Europe. We are working in shared stands in trade shows as LOPEC or Medica in Düsseldorf next month, or hopefully next year we will join many other shows after the COVID-19 is hopefully super. And just to end, there are some highlights so we can send to all of you. In this event, examples of the most advanced technologies will be heard, and we are ready to listen any idea, any challenge, any thought that you think that we want to share with us, with our members, and we are ready here to prepare new projects and new localizations. So thank you very much for being here, and thank you for listening too.
The echo problem is reducing a little bit. I would certainly ask to reduce the volume of the speakers to reduce this echo effect. So in the case of Asada Mesh, as a host of this event for several editions already, well, the idea for today was to make a welcome remarks from our president, Hideaki Asada, but unfortunately, owing to some health problems, he asked me to basically pass on to you his message. So that will help us also to compact a little bit these welcome remarks, and we go back to schedule. So actually the message is not directly from Mr. Asada, but from the vice president of the company, Hideaki Hayashi. So I'm going to pass it on to you. You all know about Asada. Thank you for coming. Thank you for following us on streaming. And I'm going to read the message, basically. Dear distinguished guests, ladies and gentlemen, thank you very much for attending the SPF 2021 workshop. His name is Hideaki Hayashi. I'm a co-CEO of Asada Mesh. It is a great pleasure for me to address you here today to celebrate the opening of the 6th annual event of the Screen Printing Forever SPF 2021 workshop. On behalf of our president, Mr. Asada, who was forced to miss today's meeting at short notice due to health reasons, we would like to express our sincere welcome to all of you. First of all, I would like to extend my deepest gratitude to Susana Otero, the head of engineering department at AIMPLAS, for granting us the great privilege of holding our screen printing workshop at the Tecnológico Institute of Plastics, and also to Susana Barasoin, manager of functional printing cluster. Thanks to their understanding and dedicated support, I'm sure that this workshop was set up so wonderfully, crossing fingers. The only regret is that I was not be allowed to travel to the wonderful land of Valencia due to travel restrictions under COVID. I miss you all so much. And of course, I'm deeply grateful to our honorable guest speakers who are setting the course of the further evolution of this private workshop. For the past decades of technological innovation, Asada Mesh, as a precision wire weaver, has worked at the forefront of electronics screen printing market, strongly believing that we have an important mission to disseminate correct knowledge and high technical potential of screen printing to the world. In this laboratory, we can exercise whole range of screen printing process from screen making, printing, and analysis to final evaluation, inviting groups of specialists from around the world. I believe this laboratory must be of great use to everybody for bringing this technology forward to its full potential. Sorry, we are talking about the OIH that most of you already know is established next to our factory in Kagoshima. Meanwhile, this annual private workshop event that we have held for the past 5 editions is what I regard as the global information hub for the latest screen printing technology, which is to be shared among these influential guests who must be playing key roles in putting the ideal screen printing practice for today's and the future generations. Although this workshop is private in nature and small in size, I place much value in deepening these precious ties between our SPF community, strengthening the network of communication among all of us, and disseminating the true nature and power of screen printing. I think we ought to get on with the honorable guest speakers presentations. So I'd like to express many thanks to Pedro for taking care for this event. And now I think it's about time to hand the stage to the honorable speakers. I would like to say once more a big welcome for all of you and those that are further from this room through the streaming. And I hope that everybody will enjoy and benefit from this event. I wish you all a very pleasant stay in Valencia, Spain. Ladies and gentlemen, thank you very much for your attention and have a nice day. Yeah, we are catching up with the time, so we are just 2 minutes behind schedule. So we will start with the first presenter today, Nicola Perinca. On stage, please. We go now with the presentation. Thank you.
Thank you, Pedro. So first of all, good morning, ladies and gentlemen. I would like to say in the first place that it's a big pleasure for us, for BC Materials, to form part of this important event. And also, we would like to kindly thank to Pedro and Asadamesh for inviting us and being able to form a part of this event. So in my talk, I'm going to talk about high-definition screen-printed interdigitated electrodes in structures for sensors and thin-film transistors. First of all, I would like to say a few words about my institution. BC Materials is a Basque Center for Materials, Application, and Nanostructures. As the name says, we are located in the Basque Country, in the north of Spain, close to Bilbao, and we are a research community of 108 researchers, and we are an international center, which means that 35% of our researchers are international researchers. Our main focus is the development of new materials. We are divided in 4 different lines and 4 different areas. The lines are the smart and active materials, micro and nanostructured materials, nano and micro devices, and advanced functional materials. And also, these lines work together to let's say, address some social economical issues within the other areas focused on the environment, energy storage, digitalization, and also the biomedicine and biotechnology. And also these lines are accompanied by 2 other lines, which is neuroscience and computational science. So to introduce my talk and the motivation of our work, as all of you know, we are living in the time of Industry 4.0 and Internet of Things. And these are based on the following principles, such as real-time operation capability, production virtualization, decentralization, decision-making by cyber-physical systems, and service-oriented software, and production according to the demand. These are also based on 3 main pillars, as I said already, Internet of Things, big data, and the safety. So all this brings us to the need of a large amount of sensors which will be implemented in the future, and precisely the printing and the printed electronics could provide a solution for these needs. So as all of you know, the printing technologies are gaining on an increasing attention due to the variety of materials which can be printed and the flexibility of the different kinds of objects and patterns, and the simple fabrication method which can be easily integrated into devices. And in terms of the flexible and printed electronics, the most important are the low-cost flexible sensors, as I have said, communication devices, and the wearables systems, which will be produced in future in a large scale. So this is the overview of the printing techniques we have available currently, such as screen printing, gravure, flexography, offset, inkjet, and recently also aerosol jet printing. In the field of printed electronics, the most extended methods are screen printing and inkjet printing. And in this talk, of course, we will focus on screen printing. When it comes to the developing of new applications using the printed electronics, it is actually a complex process where we have to take into account the inks, substrate, and printing technology interaction. When it comes to the ink, we have to deal with adjusting different physical-chemical properties, such as surface tension, viscosity, particle size, solid content, using different additives, such as viscosity modifiers, adhesion promotions, and dispersants, surfactants, and so on. It's very important also the substrate, where we have to deal with the surface properties, and of course the printing parameters and technical specification of each techniques. All these must come together and be matched well. So here I would like to explain what was our experiment in this case. The motivation comes from that the implementation of high-definition printed structures will enable to integrate printed devices at higher densities in a specific areas. And also, in case of printed sensors, we can increase the sensitivities. Apart from that, also using the screens with high definition, we can reduce the thickness. And that could bring us also to possibility of creating thin film devices, such as TFTs. And screen printing has several advantages over the other printing techniques. It is an easily upscalable printing process, and the yield is relatively high in comparison to inkjet printing when we talk about the functional inkjet printing. And also we have already quite strong market with commercial inks, which don't suffer so much from the incompatibilities. So for our experiment, we have designed such a matrix from, let's say, based on the interdigitated structures with different electrode widths and distances from 20 to 120 microns, divided by 6 steps. And as we already know, usually when it comes to printing such fine structures, we have to deal with the ink spreading. Therefore, the distance we have adjusted to 150% of the nominal line width. So for instance, for 20 microns, we had the distance of 30 microns. This is the detail of the screen of Asada mesh with the finest structure we were trying to print with a nominal width of 20 microns. Here you can see the detail of the lines of 20 micrometers with the mesh. And these are the parameters of the mesh we used. We used the mesh MS640 15CL17, which has the mesh count 640, the wire diameter 15 microns, opening area of 39%, and it was a calendared screen with the final thickness of 17 microns and the strength index of 0.73. We used the second generation of Asada mesh, which is 30%, has 30% higher tensile strength comparing to the BS type, which also makes it more, let's say, durable and provides higher dimensional accuracy. This is the comparison of different types of Asada meshes. We are here with the cycle. And also I would like to show you the details of the meshes treated by the calendar. We are in the 640, 17 microns finally. So the printing parameters we have used. We used the screen of the size of 320 by 320 millimeters, and the angle was set to 22.5 degrees. And we used the trampoline type of mesh with the inner size of 220 by 220 millimeters. The tension was set to 26 newtons per centimeter, and the air set was 2.5 more or less. The snap off we set to approximately 1 millimeter, and the printing speed was modified according to the inks we have used. We have tested first 4 different commercial inks. The 3 of them were silver-based. First, it was the Agfa SIP 2000, then it was the DuPont PE 827, and SCAG 004P from Mateprints. And last but not least, we also tested a transparent conductive ink based on P.PSS. And we used 2 different substrates, PET type. One of them is FlexTrace T24, which is a substrate suited for such applications. And also we use the standard PET for printed electronics, which is Melinex ST506, both 125 micron thick. So these are the results we have obtained with the commercial inks. First of all, we checked how all the sizes which I have specified previously been printed. And as you can see, for instance, the DuPont PE827 on the flex trace reproduces quite well the nominal thicknesses. We have the largest difference, as it will be expected, for the 20 microns. And also for 20 microns, we have observed that the lines were not continuous, which I will discuss later. The rest of the line widths from 40 to 120 were printed well, and as you can see also the ink spreading with respect to the nominal widths were very small. We were almost able to print what we attempted to print. This was the case with most of the inks we have tested, and therefore in the next slides I will focus only on 20 microns, which is actually the challenge. This is the comparison of the same combination, the same ink with the Melinex substrate. And as you can see, in terms of the ink spreading, we have observed much higher spreading on the Melinex substrate, which is something which I think needs to be dealt in future. So when we focus on 20 micron lines, this is the detail of the results on flex trace and Melinex for the ink PE827 from DuPont. And you can see that the difference with the reproduction of the line by the same ink on the two different substrates is really different. We almost received the, let's say, correct dimensions on flex trace, whereas on Melinex the lines are almost fusing and they are let's say, spreading too much according to the mesh, let's say, orientation. Also, we can see sort of pattern. We also checked the thickness, which in this case was approximately 4 micrometers and 1 micrometer in roughness. This is the result we have observed with the silver ink from Agfa, which is actually nanoparticle-based ink. And as you can see, again, we observed some discontinuities, but the let's say line width was also reproduced quite well. We have only 25 5 micron increase and 5 let's say pitch 5 micrometer pitch decrease, but still the continuity was not achieved. On the Melinex, I think this must be a mistake. It should be similar, the pitch and width size. You can see that there is not such a big difference between flex trace and Melinex substrate for this ink. So the problem of the substrate seems to be quite tackled in this case. Sorry, the thickness was approximately 2 microns and the roughness 0.7. The last silver ink we have tested is the ink from Mateprints, and also you can see that actually the 20 micrometer lines were quite well reproduced. We almost measured the 20 microns. Nevertheless, we observed some cuts and interruptions and defects, such pinholes and so on. So this is something which also still needs to be improved, but actually the result is very good in this case on a flex trace substrate. On the Melinex, it still needs to be improved, but I think the company Mateprints is just dealing with that, and maybe Aaron will discuss it later in his talk. In this case, we measured approximately 2.5 microns and 0.5 in roughness. And this is the result we have obtained with the P.PSS. we observed somewhat higher spreading of the ink, but actually we were even not expecting such a good results in terms of the line reproduction, because they were not fused, and more or less they spread significantly to up to 30 microns, and the pitch was reduced to, let's say, 10, 15 microns, but they were reproduced. We actually had more problems with the large area, which is, let's say, the support for the electrodes, which we are still investigating why this is happening. And the thickness of this layer was much lower, of course, approximately 130 nanometers and 20 nanometers in roughness. As we are actually focusing on development of new inks in BC materials, we were also keen on trying to apply some of our recent developed inks in combination with Asada mesh screens. So for these reasons, we have tested 2 different kinds of new functional inks we have developed in our center. One of them is based on the reduced graphene oxide, and the other one was based on cobalt ferrite nanoparticles. Again, we use the same substrates as previously specified. And these are the results. Just to give you an introduction of what we are actually aiming more long term, recently we have published a development of sensors precisely based on the interdigitated structures for temperature and deformation sensing based on the inks of reduced graphene oxide. In this case, it was the water-based formulation, but we have the same ink also in a solvent-based form, which is actually the one we have used. And just by easily printing the interdigitated structures, we can already directly obtain the sensors. And the challenge in this sense is the increase of the resolution of the interdigitated structures, which could help us to increase the sensitivity. So these are the results we have obtained for the reduced graphene oxide-based ink. As you can see, it was somewhat difficult to get the graphene through, so that after one print or one pass, we were not able to, let's say, print properly the graphene sheets, as they are more or less in 5 microns in size. But after the repeated prints, and due to the high dimensional stability of the Asada mesh, we are actually able to let's say, put more sheets together, graphene sheets together, so that we can obtain a certain continuity. This is, of course, accompanied with an increase of the thickness, which starts from 1.5 microns and goes up to 6, and the roughness is actually not changing significantly. The second case I was explaining was the magnetically based ink, where we also published recently an interesting work where we are trying to print interdigitated structures with conventional screens. And yeah, as you can see, we were much higher than, let's say, 100 microns, much above. And the Asada mesh could potentially help us to go below 100 microns in this case. This is the result. Again, after the repeated prints, we are able to make the let's say, printed layers more dense and almost unify the structures. In this case, it seems that actually the repeated print didn't really result in a higher thickness, but it's rather getting dense, which is good because then we can obtain a higher magnetic response. Yeah, and that's actually all. To conclude my talk, as I have explained, we were able to successfully print different kinds of functional inks, such as conductive, transparent conductive, and magnetic, with the resolution below 120 micrometers using the screen printing technique. the lines with the nominal widths of 40, 60, 80, 100, and 120 microns were continuous. However, suffering in some cases from defects such as pinholes or some other defects. And also we have observed a large difference between the substrate we have used. For the flex trace T24, we have observed that the nominal width of the lines, especially using the silver rings, is very well reproduced, whereas on the PET standard PET substrate Melinex, in some cases, as you could see, we have observed relatively high ink spreading, or even a fuse of especially the 20 micron lines. So the lines with the nominal widths of 20 microns did not result to be fully continuous in any of the cases. So it is still a challenge, which we plan to address by trying different meshes or maybe different angles. Also, I think it is somewhat related to the possibility of cleaning well the screens, as some of the openings are really small, as we are getting to the limit of the 20 microns. And also maybe the ink still needs to be slightly improved. And last but not least, we also try to print new functional inks based on the reduced graphene oxide and magnetite nanoparticles, which, as you could see, for the moment required repetitive prints to achieve, let's say, a full layer continuity. And therefore, we plan further improvements in terms of the ink formulation and development. And our outlooks are actually that as the screens based on the ASADA meshes enable to produce fine micrometric structures with the state-of-the-art conductive inks, as well as the functional new materials we are developing. This creates a base for new applications, such as sensors and transistors, which are the, let's say, needed devices for this new industry 4.0 revolution and the Internet of Things, and therefore can well address such demands, which we almost certainly will need in future. And we are planning to further improve our materials and implement them in a form of proof of concept devices in a one or a multi-layer structure, and so that we can create new applications based on our new materials. So that will be all from my side, and I thank you. And if you have any question, I will be more than happy to answer them.
Yeah, regarding the time, we just fill up the half an hour. So how about keeping the questions for the end of the panel? So for the followers on the streaming, we can continue with the timetable. Yeah, is that okay? Shall we go for taking questions after the third presentation, after the panel? Yeah. All right. So in that case, I would like to welcome Professor Günther Hübner, who will be making his presentation again in the workshop. He's being a veteran in this event, presenting in several editions. So we will adjust now the presentation and launch it. Just a minute. Okay, we're ready now.
Good morning, everyone. Avoid the echo, so I will speak very loud, and I hope that you can hear me. Yeah, once again, it's a great pleasure for me being here. I think for me it's the 5th or the 6th Screen Printing Forever workshop. And thanks to Pedro, thanks to the Asada company, I could finalize some investigation just in time, and we'll show you in a minute that some of these experiments were not possible to finalize because some of the materials were stuck in customs when they were shipped to us to Stuttgart directly from Asada company in Germany. Okay, this is our building here. And what is forward? This one in Stuttgart. No, it's not. Let's try this one. Okay. So I want to introduce to you our research institute that's located at the University in Stuttgart, the Stuttgart Media University, HDM, Hochschule der Medien. And I will shortly show a little bit what we are doing, an overview of our projects, and then I will come to my main topic, the printed batteries, and what we did here in screen printing with the help of Asada, with some Asada meshes. And this investigation is a comparison of standard PET screens with the meshes from Asada, the so-called 3D meshes. So my projects are running mostly funded by governmental calls. Here, the BMBF is the German Ministry of Education and Research, and one of them is an acronym, and we're working here on 3D forming of a carbon fiber material. And you can see here, this is a mat. It's done in a 3D forming unit. And this is a very interesting thing. The partner here is from the University of Stuttgart, where we have the application of aerospace and airplane research. And this is for lightweight materials. And so during this forming process, that's very harsh forming, we want to measure the strain that is applied to this mat. Sometimes these fibers, they will detach from each other, and so it's a one-way sensor. We print here a silver grip on this, and then it's printed on a stretchable substrate. Here TPU is used, and the thing is that these carbon fibers are conductive, so to measure the resistance, the change in resistance, that is our trick here on with this silver-based inks that we are using. Another project, and now it's coming to printed batteries. That's in the area of medicine application. It's oximetry. Basically, measure the color of the blood on the skin. Blood that is saturated with oxygen is red, and blood that is lacking oxygen is getting blue. So we're using here several LEDs, red and infrared, and a blue LED, and these are emitting light into the skin, and we have some photodiodes that measuring that. What we're doing here, this device is a patch on the skin, and we supply the printed battery that powers this patch. Very similar thing This time it's a Horizon 2020 EU project with the partners Vata, that's a battery manufacturer, and here another partner from Finland, VTT, I think well known, and another partner that mostly women know about it, partner called Swarovski. They're producing these brilliant surfaces here, and this patch is also placed on the skin. We are providing a printed battery for that, and that patch detects some physiological values and tries to calculate somehow a factor of physical well-being. And if you're feeling well, this lights up green, and if you're feeling sad or whatever, or down, that will show a red surface, maybe. So that's a very interesting project. And the fourth project we are running is 3D forming of sensors, typically for automotive application. Here you see in a door application, very small here, you can have a touch sensor, our sliders. This can either be capacitive, or in the last years we worked very hard on piezoelectric sensors for that. And this thing will be printed flat and then 3D formed. Here one more picture of this Be Well project here with this fancy surface. Here you see some skin contact sensors that measure physiological values, and here's a stack, and you have a printed battery here in the middle, and transparent perovskite solar cell above that should charge this printed battery. And for the first time, we were working very long on batteries. For the first time here, we're using the lithium-ion technology. So other projects with printed batteries were here, listed here. Print energy, we tried to print rechargeable zinc air batteries, but you have to have modified zinc for that, and the university that provided that does no longer work on that, so this is over, this project. And here capacitive sensors, also project where we tried to incorporate a printed battery in such a bionic gripper. That was also called complex systems in foil, also done. And here a lot of projects with printed batteries. And maybe 10 years ago, we had a very successful project with the printed antenna for automotive. And this is now on the market. It's a fully commercial thing. But the competition is a standard battery. One thing which is completely outside, I want to make you aware of another project we are running. It's called Print Your Future. In some countries, we face a serious problem in recruiting skilled workers for the printing industry. I'm not sure how it is in Spain, but maybe the same thing. And so there's an EU project running, and we have next week we have a final conference of this project where we want to disseminate the findings. Basically, there are not too much findings. We only see how to improve this recruiting process. Okay, now I come to these printed batteries. This is how it looks like. And we typically print on a pre-printed substrate, and the final battery looks like this. In this case, we had nickel metal hydride. We worked on this as a rechargeable battery, The problem today is that nickel is regarded as harmful, and even our partner company Vata does no longer pursue the nickel technology. So this is like completely dead. Everybody of you are aware of the advantages of printing technologies, and here, especially for the batteries, you have in classical batteries, you have rigid housings, you have no freedom of form factor. Here for printed stuff, it's bendable, you can have any shape of it, and that is a big advantage of these printed batteries. And you see, these are, let's say, competitors. The Fraunhofer in Chemnitz, they used to print batteries, and here are some others companies that if you Google for printed batteries, you find such thing, but none of them today is really, really commercial in mass production. Electrochemical systems that we're using for printed batteries, or that can be used for printed batteries, are here listed as non-rechargeable and rechargeable batteries. We call the non-rechargeable batteries a primary battery. The rechargeable battery is a secondary battery. So in this investigation, we're looking today, we're using the zinc manganese dioxide. In household systems, this system is called zinc coal or zinc carbon battery. Everyone knows this AA cell that used for home. We use the same material from the company Vata. We get this raw materials, I call it. We make it, we modify that a little bit, adding binders so that it can be printable. So it's absolutely the same material that is used in household batteries. The basic design of such a printed battery can have two types. One of them is a so-called stack design. You print one layer on top of each other, and you need two electrodes, an anode and a cathode, and in between the electrodes, in between the anode and the cathode, there must be a separating layer, and this separating layer is taking care that those electrodes are not in contact to each other. The separator is soaked in electrolyte. You can do that in printing technology, also in a coplanar design, printing the electrodes side by side and just applying an electrolyte on top of over both of them. And that is much easier to accomplish because you do not have to do some stacking, but the peak current you can get out of this is a little bit much less than here, because all the ionic transport must go over this gap. And so for better performance, the stack design is preferable. The electrode layers are typically 100 to 150 microns in thickness. The current collectors here 10 to 20 microns. And the electrolyte can either be printed, or in classical variation you have a fleece material, you soak in electrolyte and place it between the electrodes. So some of these particles are very, very coarse. The zinc particles, for instance, they can go up to 50 microns. So the only technology that is capable of doing this is screen printing. So how do we produce these printed batteries? So we have a sheet that has already a perforation here, a substrate. Then we print the current collectors, make sure that the current collectors are side by side so that you have very good way to contact this thing. It could be rectangular, this could be round shaped, any type is thinkable. Then we need a sealing, because the electrolyte is liquid, and if the electrolyte is penetrating out of this battery, that you won't have it on your skin or so. And on the other hand, it should not dry out. So we're using, for the sealing, a printable glue from our colleagues from Kissel and Wolf. And you can activate this glue afterwards by heat and pressure. So then we print the anode and cathode, and we also established a printable electrolyte. It's a gum-like electrolyte, and the last step is flapping these things together along this perforation line, and then you have then you activate the glue by heat and pressure, and then you have this printed battery. That's how we do our batteries. There's a video on YouTube where you can watch the step. One of these cells produces 1.5 volts, as in the same thing as in household. If you need higher voltage to drive electronics, you typically need 3 volts or maybe 5 volts. If you need 3 volts, you bring 2 of these cells in a series connection. Here I show 5 of them in series connection would be 7.5 volts. Typically 4 would do and have a series connection. Here in one of our former projects, this complex system in foil, we had 4 cells in a row, and you can see there were some easy printed switches, and here 2 of them are activating an LED, here 4 of them. So this can be done easily. We have an intermediate conductive path to have 3 volts or 6 volts respectively. A little bit more in detail, what we're doing with the stack design. I was always talking about the current collector. The current collector needs the smallest resistivity that you can think of, because every higher resistance would cause a lack in energy and power consumption. So this must be very conductive. So we can use silver. We know, everybody from you, that silver is the best conductive materials that you can print. However, the silver infringes with the electrochemical system. So you do not want to have a silver zinc battery. So what we have to do is we passivate the silver layer by using a carbon black layer on top of it. So that is done in order to avoid a direct contact between silver and the anode and cathode system. And this is one very important step for these printed batteries. So the carbon black needs to be very, very homogeneous, no pinholes. So sometimes we have to print this carbon black twice. So what have to be considered with printed batteries as well? I've just said about this. Silver is not electrochemically inert, so you have to overprint that with carbon black. Then the electrochemical balance in zinc manganese dioxide. This manganese dioxide is black, and some people add carbon black into that to increase conductivity. So this system is typically in household called zinc carbon or zinc coal batteries. But actually it's manganese dioxide. The manganese dioxide layer must be a little bit thicker than the zinc layer, because zinc and manganese dioxide, there's a difference in density, and the number of elements must match to each other. Then, I already mentioned this, we have to have a sealing, and one other thing, the battery zinc is not normal zinc. So there's only one company worldwide that is selling very good battery zinc, that is a company called Grillo. And they make sure that the zinc does not contain any iron. Because even some very small amounts of iron can cause that the battery doesn't work. And that was a discussion we had beforehand, because if you're using stainless steel as a mesh, could there be some abrasion or whatever? So we did not use it for the zinc layer, we used it for the manganese dioxide, because the manganese dioxide must be much thicker than the zinc layer. So we have not investigated that. Maybe this is one thing we can have a look into it in the future. If we print the zinc layer, we cover our flat bar. We have 2 AIMPLAS machines at our university. Thanks to AIMPLAS, we're using that very, very much. And so we have a plastic cap over the flat bar. Then one thing maybe I forgot to mention, the amount of electrochemical active material is responsible for the capacity of the battery. The more material you have, the higher is the capacity. And what we achieved today with this technique, I showed you about 2 to 6 milliampere hours per square centimeter. That is possible. It depends on what kind of electrolyte you're using, what kind of thickness of this material. There's one drawback. If you say, okay, I need much capacity, then I go into the height and print 5 times on top of each other, and then you have a very, very brittle layer, and then you cannot bend the battery anymore. And as you have seen for this project Oxyflex and BWell, which are behind this investigation, especially the Oxyflex, then you need the bendability to attach those patches on the skin or on somewhere here on the leg or on the arm or on the leg. So what we did now in this investigation with the ASADA mesh is we typically print the cathode material twice because we need a very thick layer. One of these target thickness is about 150 micron. That we found out that is a good thickness to achieve. And the idea is to replace the PET meshes that we're typically using by mesh from ASADA, and though we can avoid printing twice. So reduce the effort they have to do. Maybe it's a little bit more expensive, the stainless steel, than PET, but the working hours reduce them. So this was the idea. We're using this 3D mesh that has a very high thickness, and we compare it to our standard PET mesh. In this investigation, we used 2 substrates. One is a standard PET. It's the Blair, from the company Blair, the 3mm Optimum 501. It looks like this. And we used a pre-printed stuff that looks like this. Here in this pre-printed stuff that has been pre-printed on a roll-to-roll in a previous project. And the idea behind is that you can very easily have this battery that I already showed you. You only have to print the electrodes on top of it, bring in the sealing and the electrolyte, flat it together, and you have the printed battery as you have seen before. And the contacts are here on the top side. So we printed this layout here on this sheet because here we have the zinc and the manganese dioxide side by side. So these are these two substrates. Later on, remember the name Etifix. I call this substrate Etifix because the company who printed that for us, because we don't have a roll-to-roll machine at the HDM, is called Etifix. It's a label printer, 200 employees, and they have this very interesting Kaman K61 machine. It's a roll-to-roll, it's a continuous movement, but maybe you have seen the screens, they move up and down in a very strange way. My students call this a moonwalk machine. You remember Michael Jackson with his moonwalk? So it's a continuous movement, but the screen is moving backwards and forwards. That's really interesting. What we also did, all of these substrates, we treated with the atmospheric plasma. We have this system from a company called Plasma Tree, very effective. And from your talk, that one was one of the questions. Don't forget whether you have did some pre-treatment for you, and I think that's very important to do that. So we use this, as I showed you, this substrate here beneath, it's a compound foil, PET, aluminium PET. You need the aluminium for barrier properties. Just a single PET has no barrier properties. If you print the battery on this material, the battery is being dried out in a couple of days. So in order to have a shelf life of that, you need this compound material. So you print the zinc anode and the cathode, the manganese dioxide, and in the end you have this battery. So we have, hopefully you can read it. We used two meshes from Asada, 80, 225. The 225 means the thickness of the mesh, and the thread count is 35 point. The thread diameter is 31.5, and the thread count is 80 per inch. And here we have the corresponding PET, the 4380 and the 3283. Yes, with 70 microns diameter. I calculated the theoretical ink volume from the Asada meshes. It was not given on the spec chart. I calculated by multiplying the open mesh area, alpha 0, by the thickness, which is due to the standard, but it was not given. And we will see that might be not as we expect. The theoretical ink volume given in cubic centimeters per square meter typically corresponds to the expected wet layer thickness that you can print on your substrate. If you have a theoretical ink volume of 126 cubic centimeters per square meter, You can just shorten this fraction, and what comes out? Microns. Then you have 126 microns wet coating thickness. Then after drying, it shrinks because the solvent is going away. By the way, the manganese dioxide that we print is water-based. So it's about 70% solid content that we have. And what we did these 4 measures on these 2 substrates, makes 8 conditions, and we have done 4 different printing modes. Just 1 stroke and drying. Then what we typically do is in the machine, wet on wet, doing 2 strokes. And then we have the 3rd printing mode, 1 stroke, put it in the oven, dry it, then bring back into the machine, print a 2nd layer on it, and dry. The 4th printing mode is doing 2 strokes, put in the oven, and then print again 2 strokes on top of it. And so this was the layout. Then I used, this is brand new, we got it last in spring this year, a 3D, very nice 3D microscope, and I did the investigation with that, and the overall printability with the ASADA mesh was very good, also with the PET, our standard mesh was very good. So with this 3D microscope, you can see here you can produce such nice images. This is an image of the prints on the PET. This is PET. This is the manganese dioxide directly printed on PET. And here is on the Etifix substrate where the current collectors are pre-printed. You see here the substrate. Here is the current collector, and here the manganese dioxide on it. You see the surface is very rough. And so what can be done with this 3D microscope, I put in a line here, an average over this area, and so you can get a profile of the surface. Here, this is the PET substrate, and here the manganese dioxide. You cannot read it, but you can, in the software, gives you the height of this profile. And that is how I looked into that. Here you get a false color image of it. The same for this thing with the PET, the current collector, and the manganese dioxide on the pre-printed Etifix substrate. And this is the result. Here is the PET with the finer mesh. This is the PET with the coarser mesh. And this is the ASADA mesh, the coarser one, and this is the finer one. And what is very interesting, here with mode print, and these are the print modes. This is on the PET substrate, this is on the Etifix pre-printed substrate. And here, this is very interesting, on the PET substrate, you can achieve with 1 stroke almost 140 microns, layer thickness. I hope that if you, that the people in the, I think that you get these images later. Unfortunately, you cannot see that very sharp here on this screen. But this is very impressive. And what is also very impressive is that printing with 2 strokes is not very effective. Yeah, for instance, with a 2nd stroke, it could even be that we remove already deposited ink from the substrate. It lifts up again. It's not for everywhere. Here we have a little bit more. Here is almost the same, and here's almost the same. Here the same thing this is between 1 and 2 strokes. Yeah, you have a little bit more different. I have to admit that is not really statistically sound, because we did in all 64 prints, and we printed 2 sheets per setting. So, and I averaged that, but if we do a mass thing, then it could be different. But this is very interesting. So 2 strokes on top of it, 2 wet in wet, no real effect. You get really good effect if you do it a double layer. But the aim, as I said, the 150 microns, we typically have here with the 2 times printing, with the Asada mesh, it can be achieved in one single print. That was the aim of our investigation. Here you see, this is one picture of the highest deposit. Also very interesting, you have a quite rough surface, but if we use the PET, then you can see the mesh structure much more pronounced than with the Asada mesh. This was also very interesting for me. Conclusions. So, the Asada 3D Mesh 8225 is a very good alternative to the PET. But we need to do some more investigation, have a look into the roughness. For the printed batteries, the roughness is not a big problem because the electrolyte has to wet the surface, and the better the higher the surface is, the better wets the electrolyte. So roughness is not a real problem. And if we go further and print the zinc layer as well, then we have to check whether there is some infringement. Personally, I doubt. And the problem we had was we wanted to use the black mesh, which has a burnishing on it, kind of coating. And unfortunately, this one has been stuck in the customs, and it was no time to finalize. So that would be another 16 prints or so. Yeah, well, to finalize everything, the printed batteries is a rapidly growing business. I'm working now for 15 years on printed batteries, but now, next year, there will be large commercialization. If you have time, have a look on this. Elmeric is a very small company. They're using our technique in combination with Vata and us. And they have a very nice application in logistic area. There's a little video on their website. Have a look on it, and that shows how this will be. There's what is not said in this video, that there's a printed battery inside this patch, but there is one, a quite large one, and so this will be commercialized next. So I want to thank you, and of course our sponsors. We got frames from the company Hurz, because we have no, normally we stretch the screens ourselves, but in the case of the 3D mesh, we had no experience, so we asked a befriended company, the Berbertech company, and they did this for us for free. That is, I really appreciate that. And of course, we're using the Kissel and Wolf emulsions and Vata for our electrochemical materials. And that's how we test our batteries. Yeah. And I hope I have not 10 minutes late, but I hope you enjoyed this presentation. I'm open for questions after the next one.
Just 10 minutes ahead of the schedule, behind schedule. So let's move quickly. with the next speakers coming from Fraunhofer ISE. It will be Dr. Sebastian Tebner and Linda Ney. Hopefully we can go on till quarter past. Starting quarter past 10. So let's go till quarter to 11. Sorry. Yeah, go quarter of an hour into the coffee break, and then we will have time for the questions just before going for the break.
All right.
Yeah, as much as possible, because the setting is being, with that camera focusing on that area, so the sound will be better for the streamers.
Yeah, I would try to stay here in this. Okay.
Yeah, okay. Oh, okay. With these two, we compensate. Okay. Sorry.
All right. Okay. Thanks for the introduction. I have now the opportunity, together with my colleague Linda Ney, to give you an update on our research on screen printing at Fraunhofer ISE. So, in our department, production technologies, we are actually looking at very kinds of different printing technologies. Starting with standard flat-based screen printing and stencil printing. We also study rotary printing approaches and even extrusion processes like inkjet and parallel dispensing. So, the reason why we are actually studying so much printing at the Research Institute for Solar Energy is that we have to apply these metallic electrodes on the front and rear side of the solar cell to collect the current. And for that we have to print up to 120 very narrow printed fingers. We call them fingers. These are in the range of sub 30 micron in industry, and it's mainly applied by flat-based screen printing with a market share at over 95%. So here you can see the history of how the size of these electrodes have evolved by the scientific and industrial community. Over the last 15 years, we were able, in joint effort, to reduce that down to even 20 micron. In the recent years, we at Fraunhofer were able to print even below 20 microns with an aspect ratio of 1 with single-step screen printing. So the question would now be how to scale up this type of ultra-fine line screen printing approach. To study this question, we set up this type of experiment here, where you can see we set up a high-speed camera actually below the screen printing process to study how the printing fluid is actually being pushed through the screen while the flooding procedure. And here you can see some images on how that would look like, and you can see actually the rate of flooding and also the dynamics in screen snap-off actually depend on at which position we are looking in the screen opening. And this caught our attention, and we said, well, actually then we should take a closer look to how the opening architecture is actually created, right? And we said we should go beyond the standard approach of calculating the opening rate just as a percentage. We said, let's try to figure out a way that we can actually know the exact shape, the size, and the location of all these little individual openings you can see in such a screen architecture. And for that, we developed a mathematical model of the entire screen, generalized it, which is basically a convolution of a metal mesh and the layout. And by doing so, we were able to get now basically a virtual clone of any screen architecture. So you name the screen specification parameters such as mesh count, wire diameter, and so on, and we get immediately a virtual representation of that screen opening, which we can then study. For example, when you look here, you can see an example with a fairly low screen angle, and now we can see here basically plotted the opening rate, and you can see it's not a constant value anymore, it's basically changing across the opening channel. And here in this example, I mean, you can't read it now, but we have here 80% even down to 40%. So the opening rate is changing quite a bit depending on where you are in your opening channel. As you can see here, you can easily imagine that this will have a different important impact on the printing result. So we took this new algorithm we have now new data available, and we said, let's try to generalize the screen structure even more and get a quantitative measure of the utility of a screen. For that, we took this opening, the size of these individual openings, the average of that, and we put it to a ratio against the size of these individual wire bridges. Because on the one hand, they are acting as a stabilizer for the edges of the layout, but on the other hand, they are also being like flow resistant to the fluid, right? So we put the ratio of the two. Further, we have to address that depending on the angle, the number of these wire bridges actually correlate with the angle. So we have to multiply this ratio of two areas with 1 over cosine of the angle. And by doing so, we get a dimensionless parameter, which we call screen utility index, meaning we have now a parameter giving a value to the compromise between printability and stability of the screen. So let's look at some data. Here you can see on the left now the electrical resistance of these printed electrodes on a solar cell depending on the screen utility index for various kinds of different screens. And you can see there's some sort of relationship that once you go below a certain threshold, the printing becomes unstable as we have increasing mesh marks, limiting the cross-sectional area of these electrodes, and therefore the conductivity of the entire contact cleaner. Having said that, we said, well, we at Fraunhofer ISE were always using our screen printing experiments state-of-the-art screens. So we said, well, we can go back in our database now and basically rediscover the screen utility and recalculate it from old experiments, which we did. And you can see like how the screen utility index evolved over the last 10 years. And you can see with the demand of always printing narrow lines, basically you can see that the screen utility index is not really keeping up. So the screen architecture is not in the same rate keeping up as the industry demands narrow lines, right? So the question now is, well, this trend going on, screen printing at narrow lines becoming more and more challenging. What screen will be actually the best for really narrow printing? So to answer that question, we developed an evolutionary algorithm. Just as a short introduction, well, an evolutionary algorithm is based on natural selection. Basically, it's an approach which is since the 1970s has been widely used. Evolutionary and genetic algorithms are used by many scientists and engineers across many disciplines to solve all kinds of optimization problems. And we said, well, why don't we use that for screen optimization? So that's what we did. Here you can see the opening structure, and we said, well, this is some sort of a screen individual, a virtual individual, and defined by all its parameters. And these are the genes, basically. And we said, well, let's, with our algorithm, create many different screens, and they all live in a virtual environment and have to compete for survival. And competing for survival, basically, in this scenario, is screen utility. So how would that look like? Well, basically you can't read it here, but we have to define a sort of fitness, which means like we have to define what is a good screen and what is a bad screen in this virtual environment. And we said we want to have a screen utility index of 2. Also, we want to have a screen tension of at least 20 Newton per centimeter to ensure like decent snap-off mechanics. And also in this study we kept the wire material constant, which is a completely another study which could be done to open up the wire material. But in this study we kept it constant at tungsten alloy. And then we defined mathematically, we put that in an equation, and now we can basically rate these different screens. And the algorithm works fairly straightforward as an evolutionary algorithm works. You calculate the fitness for your entire population, for each individual, then you rank them, and based on their rank, they can transmit their genes to the next generation. And then you also have some sort of mutation, the chance for mutation. This, as in real evolution, this needs to be to ensure convergence of the algorithm, right? So let's take a look how that looks like. You have here 4 examples, and based on these 4 examples, this is a little game here. The bottom one would have the best fitness and would be selected as a winner in this example, and the second one would be selected as its mating partner, and the top one has, in this example, the lowest fitness, so it would be replaced by their joint offspring, right? So this is just an example. If we now look at that on a bigger scale, you can see here 3 different studies, basically. What you can see here is a mesh count wire diameter plane. So on the y-axis you have the mesh count, on the x-axis you have the wire diameter, and all these little dots are now different screens, right? As you can see here, for example. Depending on where you look, you have different screens. And we have on the left side, the challenge is to have sufficient printing at 35 micron opening, which is state-of-the-art for silicon heterojunction metallization at the moment. In the middle you have 50 micron opening, which is quite challenging, but has been done already on research level. And on the right you have some future only 9 micrometer opening printing. So again, when you look at the in the population, wherever you look, you see different screens because nothing has been not optimized yet. So when we actually start now the algorithm, you can see that as the generations go by, you can see really quickly the population converges to a species where a local optima, and then this entire species evolves over generations to account for, well, that's not working. Well, what you can see basically is it's evolving. You can see depending on what the challenge actually is, we get finer and finer mesh counts. For example, this is the result now. After 500 generations, you can see one interesting aspect that regardless of the challenge of the opening, the algorithm always has chosen an angled knotless architecture, as you can see here. It's an angled knotless architecture. We don't have any wire crossings in the channel, and the mesh is really optimized for the specific task. So when we sum that up, you can see here the industry is this curve basically indicates how the industry is expecting these printed lines to evolve over the years, and now we have basically the meshes for these predictions, like what type of meshes would be suitable for achieving even this very narrow printing. Obviously, this could be opened up. As I said, changing the wire material would open up all other new opportunities for optimization, and that's what we are working on in the future. So far, so good. This was only printing of these narrow lines. But as you can see, even in PV, the entire layout is not only consisting of straight lines, right? We have this here, the intersect between basically the bus bar and the line opening. And for printed electronics, or for no matter what of application, we actually need this algorithm to work with any layout, right? So we did that, and we developed the algorithm in a way that now you can basically take a picture of anything, load that into the algorithm, and the algorithm will create automatically a screen out of it, and then is able to optimize the screen. So as you can see here, for example, with an apple, you take an image of an apple, and immediately you get out an optimized screen with all the specification parameters. This is just an example now, but that's the workflow, how it would work like, right? So any generic image can be used to derive optimal screen candidates, and this would even work with existing screens. So the idea is that you actually you have your production process, you have your screen, you can even take out your smartphone. So the latest smartphone cameras are good enough that you can even take a picture of your screen and then reassess it and reevaluate, well, are my screen parameters even optimal for this printing task? And the algorithm will immediately gives you an indication of that. And our current plan is that we will set up at the next LOPEC conference in next spring a live demo of that. So you can, if you're attending, you can even bring some items, and we will make a picture live there at our booth, and you get immediately like your optimized screen. Right. So here I'm just showing you. We did that with we took the Asada logo from the website really quickly, and basically the algorithm is creating a screen out of that. And as you can maybe see here, this is only 3 millimeters. So printing the Asada logo at only 3 millimeters of size, we get the mesh. And here, for example, how it would look like with a 360 16 mesh. And we get all kinds of data, like a histogram on all the different individual openings, how they actually behave. And this can then be analyzed by the algorithm to find optimal parameters. And for example, the newest, the 52011 mesh then the data would completely look different. And here, I mean, you can't read it, but here is the opening rate, the average opening rate is actually better with the finer mesh. And as you can now see, here the screen angle is here 45 degrees, and when I'm clicked through these slides, you can see like the rotation, that the algorithm actually also rotates to the screen angle. Here only as an example in 5-degree steps, but the algorithm will do that much, much finer, right? So yeah, that's basically the story. At the end, before I'm giving up to Linda, I would like to put that into a little bit of a perspective, because our roadmap actually at Fraunhofer is to transition the screen printing process into the digital age. Many other industries are much further on that compared to printing, and for that we would like to develop like a full digital clone of screen printing, meaning first we have to create this digital clone for screens, and you saw the results so far on that. Also we are working on creating a digital clone for these printing fluids. And that takes a lot of investigation based on rheology and fluid dynamics. And at the end, we would like to combine those two, and we are working on that to create a completely virtual environment where you can actually run your screen printing in this virtual environment and get the results. So you can study and decide on all parameters from paste to screen what the best outcome would be. And yeah, just follow us for updates, because this roadmap basically where we are working on non-stop, and at each opportunity we are giving updates on this journey. Okay, so that's for me, and now I would like to give up to Linda.
Thank you, Sebastian. And now, coming from the digitalization, we are going to a different application, to the fuel cell fabrication. And this is kind of my topic in my PhD thesis. We are fabricating catalyst layers for fuel cells, and we are also doing this by screen printing. So just to give you a quick introduction to the fuel cells in general, this is a small sketch here. In the middle we have the heart of the fuel cell, the so-called MEA, membrane electrode assembly, and around it the bipolar plates that are distributing the different gases, oxygen and also hydrogen, around the MEA. And to focus on the fabrication of the MEA, in the middle we got the membrane, around it anode and cathode side the catalyst layers and some gas diffusion layers, and from the one hand side, from the anode comes the hydrogen, and from the other side the oxygen, and due to the electrochemical reaction we end up having an electrical current and also water which is produced. So now in general we have a trade-off in the research field of fuel cells, which is also can be applied for other technologies as well. On the one hand side we want to maximize our performance. We're using, for example, different materials, developing new ones, new cell designs. On the other hand side we want to maximize the durability of the fuel cell, which is also a great topic. For example, when we have starting and stopping of the fuel cell, we have certain stress of the material, also on the interfaces of the components. And lastly, of course, the cost we want to minimize, and therefore we have on the one hand side platinum, which is a very expensive metal in our fuel cells. So we want to reduce the amount of platinum by keeping the highest performance possible. And also the second point where we can reduce the cost is the upscaling of the manufacturing process. And at the moment we are here a little bit lacking, because this is still kind of in the laboratory scale. So the upscaling needs to be like researched a little bit more and looked deeper into it. So the main challenges here are the upscaling problems. Just have a quick view deep into the catalyst layers that we are producing. This is a very porous structure. You can see here in the SEM image, we have a carbon support, a carbon black, where nanometer particles are on it. For the electrical connectivity, the ionomer network, which is a binder and also conducting the protons. And we got the pore network so that all the gases can actually diffuse through the pores and reaching the platinum for the electrochemical reaction. So when we are fabricating this, we have the three components, the platinum on carbon powder, ionomer, and also some solvents. We are mixing it up to get a paste, and then we are doing flatbed screen printing. Here we are printing on a so-called transfer foil, which is later on not included in a fuel cell. We are drying it, and then we're having a hot pressing step where you're putting anode and cathode side together on the membrane, removing the transfer foil, and end up with our fuel cell that we can test under operation. And especially for the flatbed screen printing, we have our PVTech, where we usually do it for solar cells. We have 2 industrial screen printing lines, which is really nice that we can now profit from the experience here from the solar cell side and use it also for the fuel cell fabrication. So just to have a quick look how this looks like, our catalyst ink production in a glove box system. We're doing the flatbed screen printing here. Usually we are printing homogeneous layers, drying them and hot pressing them. So at the end we are ending up with a catalyst coated membrane full area here of 12 square centimeters. In general, when we have a printing process, it's very important to also check out the rheology of our catalyst inks. Therefore, we're using rotational rheometer that we can see here. And basically, since we are doing our own paste, we can design our paste how we want it for different coating methods. And when we're using screen printing and having higher solid contents, we end up having a strongly shear thinning behavior of our catalyst inks. When we first tried out the screen printing process, we varied different parameters. For example, we used different meshes, from coarse to fine meshes, and we end up adjusting quite good the layer weight that we got. So, for example, on the cathode side and anode side, we need different layer weights and layer thicknesses. So therefore, we could use different screens in our process. We varied also the squeegee pressure. In this range here, it has had no really significant effect on the layer weight, and we also varied the squeegee velocity, whereas the velocity in this case had not such a trend that we expected, but if we have a look, for example, on the height that we printed, on the thickness of the layer, we could see that for here, increasing the velocity of the squeegee, we end up having smaller arrow bars. So we are printing more homogeneously layers. Was our conclusion here was that we need to have a better dispersing process actually for our paste, because when we're having a higher velocity of printing, we're having a higher shear rate and therefore are breaking up the agglomerates, and therefore we have to go a step back and need to revise our dispersion process even more and enhance it. So having done some printing processes, we had 2 different pastes actually, a water-based one and one without water. And what we could see with the number of prints, that the platinum loading, which is also equivalent with a layer weight that we printed, is getting higher and higher with the number of prints. So our paste actually is not stable for screen printing, it evaporates during the printing process. And with water, it evaporates even more. And therefore, we need to look into different solvents that we can use to make the paste more stable. But changing the solvents could also have an effect on the performance of the fuel cell. So, for example, here, this is a typical performance curve. We could see having water or not water in our paste actually has a dependent or has a small difference in the performance, but on cell level, a small difference can be a big difference on stack level, actually. So what we did, we checked up different solvents in our paste, kind of standard solvents that we had also known from literature, And these solvents gave us also different rheological behavior. What you can see here in the laser scanning images and the heat map, for example, octanol and heptanol, both of them you can see that the mesh marks are actually on the surface of the layer, which has two reasons. One reason for octanol is that octanol has a very high dynamic yield stress that we measured in oscillatory measurements from rheology, and heptanol has a very strong thixotropic behavior. So when we are printing and right after drying, we're kind of freezing the structure, and the structure has not enough time to build up its structures and get homogeneous. So we also tested them in our test benches, get the performance curves, and we end up having selected now a very good solvent which had the best performance, and also here on the right hand side had the best stability during the screen printing process. So and with this new ink recipe, we at the first hand side printed only large layers or full areas, but what we also could do is structuring actually. Structuring could be also a very good idea in terms of fabricating the catalyst layers. As you can remember, we have the bipolar plates that have different structures of the gas distribution, and they can get quite a complex actually. We have channels and we have ribs where the gas is flowing through, and when you look at the heat map here, how the oxygen gas is distributed along these channels. At the inlet we have a high concentration of oxygen, and towards the outlet it gets consumed by the electrochemical reaction. So you can see this kind of gradient here. And this gradient also results in having different current densities from inlet to outlet. And different current densities means also different temperature distributions. And this can lead actually to a mechanical stress of all the components if the temperature is quite different at different parts of the fuel cell, and therefore also a faster degradation. So what the idea could be here, how to solve this distribution problem, we could actually print the catalyst layer in a segmented way with different pastes to invert the problem with the inhomogeneous distribution. For example, in the segment 1, we could print a paste which has less platinum in it and going up to higher platinum. Or what we can also do, if we look at even more complex structures of the flow fields, you can see there is a higher difference in the current density, like from very red to deep blue. We could also imitate the structure of the flow field actually, and print two pastes next to each other, like to get the in-plane structure as well on the catalyst layers. And the beneficial thing that we are trying to get here, like the aim of it, could be that we reduce the amount of platinum on the one hand side to get a cheaper fuel cell, or even making the fuel cell more homogeneous and the reactions more homogeneous. And yeah, which coating method could be here suitable? We need a high throughput, high layer thickness, and a very precise alignment. And there are so many technologies. Also in the field of fuel cells, we have slot die coatings, which is the common thing in industry, but also in research, spray coating, inkjet printing, electrospinning, and also the rotational technologies. And what we choose in here, it could be also others like gravure printing or flexographic printing. What we've chosen is the flatbed screen printing, and we designed a test structure for starters to see if our new developed ink is able to even print fine lines. And actually it was a quite nice result that we are able to have different structures also with the catalyst inks that we designed. And the next steps would be now that we are imitating the flow field and printing two different pastes with and without platinum next to each other to end up having cheaper or reduced platinum loading at the same performance level. Yeah, and that's all from my side. Thanks for your attention, and if you have questions.
Well, thank you very much for compacting your time. So we have some extra minutes to take questions before going to the. I mean, the idea was to go at 10:30 to the break, but we said that we will take a quarter of an hour. So maybe if there is some questions for the presentations before, we can go with some of them. Or if you prefer, just just take a rest and have a coffee and eventually discuss outside. Yeah. Okay.
Already said the question to Nicola, so he already answered.
Yeah. Yeah. Do you want to?
It was about did you did some pre-treatment of your substrates?
Yeah, it's a nice question. We actually didn't, but of course we know that there is a possibility of using the treatment by plasma or other techniques. But the fact is that the two substrates we used are actually sort of ready to use, because the Melinex ST506 is already pre-treated substrate.
Yes,
and normally we use it without. And also I have some negative experience sometimes with using the ozone treatment, because actually then it becomes the opposite, that the ink spreads too much. So yeah, I think it's an important point. We could extend our experiment, but also due to the lack of time we had in this case, we did not include it as another variable. But yeah, in future, it's interesting.
Yeah, it's very
to add this parameter.
Just a comment from my side. We had also, I'm not really sure remember which one, but we had a pre-treated polyester, and it worked well. We printed, everything adhered very well, and 1 week later everything started to delaminate. So to avoid this, we used this untreated mylar that worked in this case very well. So this treatment, nobody knows what the manufacturer does.
Yeah, it's true.
Yeah, actually, it's very interesting that also my colleague Fernando Zicarelli is conducting a sort of systematic study approaching, what is in the market. In this case, for treated substrates, to try to establish, the benchmark regarding to that, because as you say, it's a kind of mystery what the manufacturers does with the substrates, and the promise is always, wonderful, but it can create some confusion in the industry if we don't properly benchmark. So, tomorrow will be a little bit of a presentation from him. Will be a compact presentation from him related to that study, and he is ongoing with further experiments. So hopefully by the end of this year we will have, some more conclusions.
Yeah.
Okay. If there is any other?
Any other question for Nicola Brinker? Nope. Any question for? Okay. I'm sorry.
Magnetic properties in interdigitated system. Do you have an application in mind?
Well, here the aim is to microstructure the magnetic ink, because like that we can create new kinds of applications where the magnets are needed.
Memories, or?
For instance. Yeah. Then you can think of whatever you want where the magnets are applied. But the idea was here to go beyond what we have published previously in our paper and to reduce the size, so that we can attempt other applications.
As you said yesterday, miniaturization is a nice goal. In standard electronics, it might be also a nice goal to follow in printed electronics. Is any other question among the audience for Dr. Nicola Brinker? No? Maybe questions for the second presentation for Professor Gunther Hubner? Yep. broadcast on YouTube, so I'm checking if messages come from. I haven't seen any. So, any further question for Professor Gunther's presentation among the audience in the room? No? So, shall we move to questions on the presentation of Dr. Tebner and Mrs. Ney? Yep.
What's with the emulsion buildup over mesh? You also able to include this in this algorithm? Or did I miss something?
Yeah, we are currently working on making the entire model.
If you could, stand up and because people at the back will not listen.
Yeah, sure. So yeah, we are working on making the model go 3D, so the EOM will be also very constant. Also all the different kinds of different meshes, right? If we have 3D mesh, at the end of the day, the algorithm should be able to handle all kinds of products. And even options which are not new products yet.
Okay. Any question? Any further question for Mr. Tebner, or eventually about the fuel cells? The very interesting presentation about fuel cells that Linda gave to us. Okay, I have one for Linda. Basically, is very interesting the comments you made about reduce the cost of the fuel cells by applying different patterns that eventually are suitable to being screen printed. So could you elaborate a little bit more? I mean, what is the situation till now with the field and with other coating technologies, and your idea to go forward with screen printing to achieve certain patterns and so on?
So like the industry standard, as I would say, is currently slot die coating, since they're just applying the full area layout. This is like the more or less straightforward approach to build up the fuel cells. But still, if you look at the cost distribution of the whole fuel cell materials, the catalyst layer with the platinum has a really large percentage. Like the material cost is very high here. So any approach to reduce this kind of cost for the materials is beneficial actually, and also is has more impact than changing the coating method actually. So of course with screen printing we have like the consumable screens that have a certain lifetime that needs to be replaced from time to time, but still, like in the diagram of costs, the majority or the major costs are still the materials. So keeping down the platinum amount is like the way to go actually. Yeah, but still also some other applications could be imaginable. Actually, it's not often done, like the flexographic printing is not that much distributed in literature. We have still very low layer thicknesses. So that's why it's probably not that common. But with screen printing, we can reach up really high thicknesses, which is probably the case also in other applications like for batteries. So therefore, screen printing could be a good choice.
Okay. Yeah. Thank you very much. So we are, within this extended time for going for the break. So we'll have now the possibility to take a coffee and just keep chatting a little bit, but also looking at the tabletop exhibits outside. So we will be back at 11:30. So try to get in track with the back in track with the schedule that you have in your hands. Okay. Thank you. Okay, thank you very much for your attention throughout the presentations in the morning and the very active networking chance we have over the break for the coffee. Now we will restart with the conference of this morning, and we will go with a panel of 3 companies. So the previous panel was assembling a view of the cutting-edge research, and now we will be having speakers from the industry. So we will see also the perspective of companies who are actually making sales of products for the screen printing, for the advanced screen printing. First conference will go on behalf of Kiesel & Wolf Group, well known in the screen printing business as emulsion producers, but they also, well, they have general chemical products like adhesives and so on. They will explain better. And I hope you can enjoy the second part of the conference too. So I'm just handing the stage to Andreas Kunkele and Simon Wagner.
Thank you, Pedro. Welcome in the name of Kiesel & Wolf. Many thanks to Asada and all the other participants. It is a pleasure for us to be here and to introduce our fine line program and current findings. I don't want to talk so much about Kivo, but yeah, we are the leading producers of printing form chemicals for screen and textile printing. And now we have a full range of products for screen printing making, for stencil making, mesh treatment, cleaning, mesh, and post-treatment and auxiliary products. Additionally, we also provide a wide range of adhesives, resists, and coatings, even for the electronic industry. All this is delivered in a worldwide service and local technical liaison staff wherever possible, with distribution partners and end users can therefore always rely on our know-how also on site. And yeah, Pedro already told, I'm Andreas and that's Simon Wagner. And I'm from the Applications Technology Laboratory, and Simon is from the Research and Development Department on the emulsion and chemistry side. We prepared for you a small agenda for today. First of all, an update on our fine line stencil making for printed electronics. A small part, the most suitable prepress for printed electronics. And at the end, the latest trials regarding the durability of printing stencils treated with our release agent. And at least a summary out of this. And now I hand over to my colleague, Simon Wagner.
Thanks. To give you a guideline, we first introduce you like the fine line screen printing stencil that we recommend for the perfect printing result with our chemicals. And therefore, we introduce you at the end how that results in a printing line. You can see it here on the right bottom. And Andreas will show you how it's scalable for the industry application. At the first, I hope you can see it in the pictures here. Maybe I can also magnify that. You can hear the first one, the base for a perfect stencil is the emulsion with the highest resolution, depending on the demand or the requirement. And exactly, for the second one, it's the post-coating. It's to reduce the RZ value and the mechanical resistance, and that also is good for the better printing result. And at the third point, we are going to optimizing paste release with our auxiliary products, and that is also the main focus of our today's presentation. And Andreas will show you the application tests to the latest results of that. here to give you a short view how that all results. Here you got 25 micron lines ending in a bus bar, printed on a silicon wafer, and made with a Kivu stencil. So to give you a hint or a better understanding about the differences about a in comparison to our fine line emulsions, here on the left side you can see conventional SPQ photo emulsion with a coarse distribution and undefined printing edge. At Yaso photo emulsion is quite better, but in the right picture you can see our fine line photo emulsion. You can see here a sharp printing channel and a defined printing edge, and even a smoother and even EOM than it's possible with the most conventional diazo photo emulsions. The first one I want to introduce is the Acicos 177FL. You can see the SEM picture on the right side. It's a solvent and water resistant emulsion. You can see the sharp printing edge in channel, and the possible resolution is 20 microns, but it depends on the EOM. If you got fine lines down under, it's possible to go to 10 or 5 microns, but therefore just the EOM of 2 or 3 microns. So this is also the recommendation of us for the most applications in printed electronics, higher printed line width, and just below 10 micron. If you want really fine lines at a EOM over 10 microns, we recommend our next product. That is our current development and state of the art of the fine line program. It's possible to get a good fine line about 20 microns at an EOM of 20 microns. That is the state of the art. Maybe you can also magnify that pictures. And that's a SEM picture, and you can see on the left side the EOM of 20 microns, and also the positive and negative lines are nearly to that state. The special thing about the Z173-1 FLH, the H stands for hardenable. It's developed for especially the solar industry. You can post-hardening it, and it's possible to get about 30,000 printing strokes and with a good printing quality. So here's just a short view for what it is necessary. Edge sharpness and the sharp printing edge is not just an optical thing. It also results in a good ink release and a good printing result. And as I told you before, here are the possible resolutions we can achieve with our emulsions depending on the EOM. We have here a 10 micron negative line, and here a 5 micron positive line. Let's come to the second part to make the perfect stencil. It's post-coating. We therefore have the product, the Estelan D271 top coat. And it's a chemical bonding on the emulsion after exposure. And you can reduce the RZ value with that one. And reduce of the RZ value results in a better printing quality. You can increase the chemical resistance, especially for solvent cleaners in cleaning processes. And it's also suitable not for the fine line program. It's generally for graphic applications. You can apply that on normal conventional screen printing emulsions. Especially for the solar industry, this one also, we call it like bulletproof effect. Maybe you can see it in the pictures. Here is it without the post-coating. You've got slight defects in the surface, and with the post-coating, you've got a smooth, even surface, resulting in a better printing results. And you also have like heights on the silicon wafer or abrasive parts in the ink, and therefore it's getting better prevented for damages. Also part of the post-coating I already told is the Kivu ZFL. and therefore it's also like you apply it on the screen afterwards, and therefore it's possible to make like 3,000 printing strokes. And the picture on the right side is after cleaning with EPA and ethanol, and you see that you still have a smooth fine line that is still stable. So they come to our newest development on making the perfect stencil for printed electronics. It's the KivoMix RA7015, and we developed a better application method. Now it's a spray coating method, and we got good results with that. Andreas will tell you later. You get a better printing release during the printing process, and especially for the solar industry, the high aspect ratio increases significantly. You get a better topography, less or no bleeding effects, especially when you're cleaning, and also for like working breaks during the industry process, you got less clogging effects. And here on the right side, you can see with our product Z177FL, the printing channel without cleaning, and you got a lot of residues of the silver ink. And when you see the applied surface modification with the KivoMix, there are nearly no residues of the ink, so you also got cost reduce of the silver paste. It's a chemical cross-linking for the emulsion surface, so it's a long-lasting effect, and we proved that in application tests. Andreas will tell you later. So the first thing we want to prove if it's really reliable or if we got improvement of that ink release effect, we measured like the surface tension. And the Acecal Z305FL is the first conventional diazo emulsion we had for our fine line program. Got the contact angle for water for the boiler. The glass master to get the best printing edge definition, and for the printing here we got after the exposure a 20 micron EUM with 2.3 micron RZ-way. And here's the result. We have here a 20 micron line on the left side. You can see it without the release agent, and you got like narrow parts here and also valleys. And here is the 20 micron line with the release agent, and it's more smooth and even. And yeah, so the effect was proven in research and development. And here are also some pictures resulting in that. We got here like the 25 micron lines seen before, ending in the bus bar, and also like on coarse surfaces like silicon wafers, you got a smooth line of the 25 micron line also in the topography of the conduct finger. So to give you a hint what is maybe possible in the future with our product line, on the left side you can see the current state of the Z173/1 FLH. I told you that the state is you can reproduce a 20 micron EUM with a 20 micron line width. But if you want smaller line width, you can see that you got bridges in the printing channel, which result in a bad printing result. And the new development should achieve a 15 micron line width with an EUM of 15 micron. And that's where we're working at. And now I hand over to Andreas, who will tell you about the best suitable thin template for printed electronics.
So that's always a discussion, I would say. Yeah, when we talk about fine line, we have to imagine or we have to think about what is fine line, when fine line starts. And for us at Kibo, maybe for Asada as well, fine line anymore. Yeah. And before I start the latest findings, I want to just talk a little bit about these possibilities, what we see for the electronic printing. And as you can see here in the first picture, we talk about below 2,400 dpi in the direction of 2,600 dpi, and we see a very poor edge definition in such performed prepress films. And we think this is not the best. And out of our experience for fine line processing with prepress, it starts with 60,000 dpi, as you can see here. And it's also a question of the proportion of the line widths in different angles. So we have not only the 0 degrees or the 90 degrees layouts, we have also angles or circles and so on. And we think the proportion, they should stay stable. And if it is really high end, we would also say more in the direction, to go in the direction of 200,000 dpi, possible with a Glassmaster prepress. But this is also a question of demand and of costs by the end. And I forgot to tell, I go once more back. I forgot to tell, it's also a question of availability of the prepress manufacturers or the repro studios. They able to supply you such a good quality. So I think also this is also a big question, because even the chemistry behind the lithofilms, maybe the quality will be not the same in the future as it is at the moment. And yeah, because this business for the screen printing is so small, and yeah, so we have to think about this as well. I have to make a step back. In our former project, we present together with Asada and with the Fraunhofer ISE and with Sun Chemical. We had a project together, and we want to see the effect of our release agent in conductive ultra-fine lines, and therefore I want to give you just a brief insight of this project. So the target was to print the 20 micron line, and therefore we made a stencil. Here you can see with a 25 micron line width we exposed on it. On squeegee side it was a little bit wider. This is a behavior we face in such an exposure processing with a wire mesh, because yeah, there's a lot of energy is absorbed, and that's why it's getting wider on the squeegee side. And what we see here also is the so-called cuboid effect. And it's also a behavior we face if we expose a wire mesh, because the wire, there is no light coming through, it's coming only around the thread. And that's why it is like this, that if you have a correct exposure time, that is like a cuboid you have on visible on squeegee side. But it's a good thing, because it's even surface, and you have not so much relays, so it's uniform with the treat topic or the crossing topic of the wire, and so you save also the consumption of pastes by the end. And then we are able, so we made two stencils. We made one stencil with release agent and one stencil without release agent. And here are on the left side, you have the print result with the stencil with release agent, and on the right side, you have the result without release agent. And as you can see here, there are really narrow places in this conductor track, and the stencil we made with release agent achieves in the print result by the end much more homogeneous track at the end. And that was really nice to see. At the end, we made, out of this project, we made a summary. So we did not only print a 20 micron track, we did also print a 30 micron and a 40 micron track to get more data. And as you can see, all the bars with the release agent in this graph show a reduction of resistance in comparison to print bars without release agent. So somehow it's a little bit linear. One question out of this test project was, at the end, at the last discussion, how is the durability of our release agent in a higher print run? That's why we did the following tests. And the goal setting of this test, the aim of this test project, if the surface treatment with our release agent, Mix, retained on the stencil surface after a longer print run process. And therefore, we made 2 stencils, and we made 5,000 squeegee cycles to check this before and after. And we made a stencil. We take a SADA mesh. It's not the finest, but you know, if you do such a long print run test, you have to be safe on the side that it don't scratch and that it keeps for this testing. The margin was the article Z173/1 FLH. And I don't want to read all the numbers. Maybe interesting is also the EOM. We achieved 8 micron EOM. We think this is a good EOM for printed electronics, and RC value of 4 micron. And then we checked the surface energy before this print run test, and we made SEM pictures. On the left side, you see the stencil made without with release agent. On the right side, you see the stencil or the SEM pictures without release agent. And yeah, these values here, these numbers we noticed, and to compare it later on after the printing stroke test. And yeah, we did the print run test with our Time 3010H in our lab. And yeah, I don't want to read all the parameters, but we had a RKS 75 Shore, and we had a silver paste from Henkel Loctite, the ACI 1010. And as I said before, we did 5,000 strokes, and we use a cleaner out of the Kivo program for the cleaning in between and also for the end using. After the print run, we checked the surface tension of each stencil with and without release agent once again. Regarding the abrasion and the mechanical influence after this print run of 5,000 strokes, we observed just a slightly changes of the values of the surface tension and contact angles. Therefore, a good stability of the surface modification is given. As you can see, out of the praxis, cleaning after the print run, there are much more silver paste residues at the SEM pictures on the right side without release agent. Here on the squeegee side, you see it. Maybe very good. Maybe I can make a magnification on it. Yeah. If we move here, you see here are much less residues than on this side with the silver paste at the end. For comparison, we summarize the values before and after print run from printing and squeegee side. On this file, you see only the values of the printing side, and the variation of the values before and after the print run just slightly changed from here to here. On this file are the values of the squeegee side regarding that one squeegee side is much more mechanical abrasion given. Once more, the variation of the values before and after print run just slightly changed, as you can see from here to here and from here to here. I don't want to read all the numbers, but we are really happy to see such a good result. And we did additionally a print test after this 5,000 strokes to check also the quality of the shape. And yeah, here you see the pictures with release agent, and here you see the printed pictures without release agent. And yeah, the topography and also if you look from top on it, the shape and also the topography, the valleys are much less with the release agent than it is without release agent. And also regarding, we did the ohm measurement. We take a 30 millimeter track and measured only the ohm, not the ohm meter or something like this. But we see also regarding this, we see 11.3% less by using the stencil with release agent, and check the print result at the end. As a summary, we can say the surface treatment holds up very well after more than 5,000 printing cycles, and also verifiable present after the end of printing. Our fine line emulsion are in combination with our release agent Mix, surface modification suitable for an optimized process reliability in printed electronics. In addition, the stencil resistance has significantly improved by the surface treatment, even beyond addition of 5,000. So now I'm on the end. I have only one hint for you. Since the end of August, we are a cooperation partner with Henkel Loctite, Kivo, in direct sales. But to be honest, it's not nice for Spain, but it's limited. So we operate with them only in Germany, Austria, and Swiss. But if someone needs something, I'm also happy to forward to someone else at Henkel Loctite if there are some needs and so on. And yeah, we are exclusively work with them together because we are very well in the screen printing industry with stencil making and so on. And we think it's a good combination to have this cooperation. And yeah, we provide with them the silver paste, the electricum printing medias, and yeah, so these are only for the screen printing. They have other products for sure, but we are concentrate on the screen printing segment. And now we are on the end, and we are happy for your questions or for the discussion later on at the tabletop.
Okay. I think we are doing well with the time. Yeah, just a second. It will be next ECRA, but they told me that they have a little bit shorter presentation, so we can go with questions. I think Professor Hubner wants to make a question.
Comment. If you're using this measurement of the surface tension of a solid, you're using only two test liquids, water and methane, and you're getting results of 9 or 10 millinewtons per meter. That is much too low. You have to maybe think about using the Owens-Ventrabel-Kelble method in the full variant with using 4 or 5 test liquid because this value is not reliable. What you have definitely shown is there's an effect, and that is a very good effect. But to be scientifically correct, I would recommend using at least 4 or 5 test liquids.
So it makes the data more reliable. I agree to you, but for the test it was quite okay to prove that effect. And I think also in a like scientific way you can prove that it's a relative value. But it's like the Kibomix is based on like nanotechnology, and therefore it's really maybe not that low, but there are values that possible at that rate, even under 50 microns, 15 millinewton per meter. It's possible.
So Teflon has 17, and Teflon is the material with the lowest value. So.
Yeah, but there are really studies that prove that effect that could be below 15 times.
Don't use dimes.
Yeah. But I agree to you that it's
but important is also that we not use only water angle, because hydrophobic behavior is not what we want. We want oleophobic behavior.
Sure.
Okay. Is there any other question for the presenters from Kisling-Wolf? If not, we can just move on to the next presentation. So if people from ECRA come to the stage.
Funciona esto, ¿no? ¿Sí va? Sí, va.
So now we will go with the fifth presentation of this morning. It will be on behalf of ASIS Group and the screen printing manufacturer, screen printing equipment manufacturer of the group, ECRA. We'll have two speakers, joining for the presentation. Is Sergio Rico, is the sales representative of ASIS Group in Spain and Portugal. But also we have the collaboration of Ricardo Martinez, who is actually working on applications. He's an application engineer directly on the factory at the factory of Bolingen of ECRA. So I hope you enjoy also this presentation, and I just hand the stage to Sergio.
Thank you, Pedro. So good afternoon to everyone, and we will be introducing ECRA. I will be placing it in context inside ASIS Group. And as Pedro said, I'm Sergio Rico, the sales manager. I'm covering the Iberian market, Spain and Portugal, for the complete ASIS Group. And then Ricardo Martinez is from ECRA, from the HICON department, the application team. He will be focusing on more technical details. But first of all, thank you very much, Pedro and Asada, for this event, and as well to AIMPLAS and the cluster for allowing us to be here today. So, first, ECRA, it was created a long time ago. It's a company manufacturing printers, and it was established in it started in 1976, manufacturing the first printers in the market. So there is a long history, quite a lot of knowledge related to the printing systems. In 2005, it was bought by the ASIS Group, and now it's part of the ASIS Group, which is involved in around 10 companies, all related to the electronic industry, mainly electronic, solar business, and nowadays as well to the health sector, okay, biomedical, and life science. So in Access Group, in ECRA, we have the printers. You already, or most of you already know them. And then in the Access Group, we have many other solutions like handling, material logistics, laser marking for traceability. We have also the paneling system to cut the PCBs, to individualize the substrates into single ones. We have also all kind of tray, handling system, tray system, and also one other important, or you might find more interesting, is the clean room solutions. Not only the complete clean room, but also individual clean desk with laminar flow. So if you have products which cannot contain or have any particles, we can also provide this solution in an individual desk on the shop floor. Okay, so with the wide range of products that we can provide, we cover the electronic print area. Most of the solutions are related to the PCB manufacturing sites, but we also have solutions for wafer printer, solar cells printing as well, and inside that huge market we have one specific, which is the conductive circuits. Conductive circuits are mainly done on hybrids, on ceramics. This is a rigid substrate, and we print layer over layer, creating the circuits. Then after that, some components can be mounted as well to have some similar solution like a standard PCB. And within that segment, we find the printed electronics, which is the focus today, the focus topic today. So, I don't know what's going on. In this printed electronics, we find that it's a very competitive solution. It can be cost effective because it's very cheap to produce and to process. We can find very thin substrates which make it flexible as well for many different integrations. But what can ECRA offer to produce such substrates or to process those flexible foils on flexible substrates? First, as we will see today later, we have the semi-automatic printers. These are the most basic machines, but the most flexible ones as well. So in this case, someone, an operator, has to load and unload the substrates. And we can print with the screens or also with the stencils. This is the starting point. We can use those printers for manufacturing as well, not only for testing or for labs. We can go to the next step, which is the offline automatic. The machines or the solutions look quite similar, but there is a huge difference, which is the camera system. In this case, the camera is detecting fiducials automatically. So that will make life much easier for the operators or for the tests as well. The next step will be inline automatic printers. That means no operator needed in front of the printer. Someone will have to load. Oh, sorry for this, I don't know what's going on. Someone has to load a stack of substrates or a magazine with substrates, and at the end collect those substrates or those products already finished in a stack or in a magazine as well. And finally, when production must be brought to a very, very high level, we have reel-to-reel solutions. So in that case, we can have a huge production, mass production of the same items, going from roll to roll at the end, but using the same type of printers as in line. Always a flat surface, moving parts. So that was a question before. How do we go from lab to production? We can cover all steps in that. And now the next question is, how does screen printing work? Because, okay, the printers we have can be used for stencil printing or for screen printing. We have seen many times today these kind of images with a mesh. And as well, we have heard we need to use some ink, some paste, squeegees. How does it work? Well, maybe you know you are already used to work with printers, but in case someone is not very used to this process, we need to consider several items. First of all, starting from below, we have the substrate, and which can be of any kind, any thickness, any material, I mean. Below this substrate, we have a support system, which is very important to support it correctly and do the printing process later on. And above it, we have the screen, which is represented by those circles. We can see this image. So on top of this screen, we have to dispense the ink, the paste. And then on top of it, we will have the flat squeegees and the rubber squeegees. So with that paste, usually the process should start on this side. For this drawing, we will have the paste. The squeegee will be pushing this paste through the holes on the screen, touching it lightly, the substrate, and the paste will be dispensed on the substrate itself. Then the screen has some flexibility, it will go to the right place. There will be always a gap between the screen and the substrate. So at the end, it will be separated, and we will keep this ink or paste on the substrate. So as you see, there are many factors at this point which makes screen or printing process a little bit difficult. We have to consider what type of substrate we have, type of ink, mesh, and the squeegees. But screen printing is a very, let's say, it has some advantages, and very good advantages. First one is the flexibility compared to other printing methods. And second one is the speed. So why flexibility? Because we can handle many types of substrates. Not only one material, it can be any material. We can have also as well different thicknesses for this substrate. As well, we can control how much ink or paste can be dispensed on top of the substrate. We can go to very small substrates or larger ones. As well, we can print any type of layout on this substrate. We see it here, I forgot to mention before, we have the mesh, and on top of the mesh we have this emulsion, which will prevent the paste or ink to go through the holes, and at the end we will have the result that we want to print. And then about speed. We can increase cycle times, and we can print any shape. We can also bring small pieces together in a carrier and print them together, so that will make the process much faster at the end. So if you want to have a product of 10 by 10 millimeters, you don't need to print one by one. You can bring all of them together and get a final product. Okay, but that I have introduced some good things about printing. It can be faster, but at the same time, we have some challenges. And one of the first challenge is we find it when we want to print layer over layer. In that case, we need to use fiducials. Fiducials are marks that we print on the corners, usually on the corners of the substrates, and we use that mark to align layer over layer. For that purpose, we use a camera system. So we will see later today that in offline and semi-automatic printers, we have external cameras, but in inline systems, we have an internal camera, which is placed between the substrate and the screen. We have two cameras, one looking up, one looking down. They will detect the fiducials and will align the base, the plate with the screen. But problems may arise when we have different kind of substrates, such as FR4 or dark different colors, or even transparent ones. And for that, we also have solutions. We can change the camera, the illumination. We can use the type of illumination, direct and indirect. And we can also use polarized light. In this way, we will be able to detect the fiducials and do a fast process. And of course, print layer over a layer accurately. So we have some images here of fiducials and so on. And there are some other issues that may arise. I will let my colleague continue with more technical details, and as well with the tests.
So yeah, I'm Ricardo Martinez from ECRA, and yeah, well, when we are talking about flexible electronics, we are talking often about PET or maybe things like Capstone. So we could have problems, for example, when you have to dry your substrate. After drying, you get a shrinkage of the substrate because of the temperature. So either you wait a long time until it's stretched back, but you don't know if it will stretch the same way. So what we will do is we will have several points on the substrate where we measure the fiducials, and we will adjust them as good as possible. So what can happen also? Maybe your substrate doesn't have any fiducials, it doesn't have anything. Maybe you have something like this, a blank ceramic, and you want to print something over it. How can I do it? You can also use, for example, the edges to align to each other. Or you have shrinkage, and there is an offset, of course, of the one print to the second one because of this variable size. So we also have the possibility to adjust it manually and also sometimes automatically, depending if you have on the line SPI, for example, so an inspection system. We conducted a small experiment. So we are a screen printer manufacturer. We are not a lab, but still we have some facilities where we can print some small batches. Also in this case we printed with well, offline automatic is maybe a little bit of a weird name. It's actually a half automatic with an automatic alignment that we use for this example here. So what we did, we used mesh from Asada and HSD 65014, and also some squeegees for RKS carbon 80 Shore, then printed on different substrates, for example, printed on some LTCC, so this is ceramic, which are not sintered yet, so it's still flexible. We printed on Kapton foils, we printed on rigid ceramics, on PET, and using the same mesh, using different inks, we just checked how does it look after we print. Because of course, you have high quality mesh, you have a high quality printer, you have high quality squeegees, but at the end, if everything doesn't work together, for example, the ink with the surface energy of the different substrates afterwards, then you won't get a good result. Doesn't matter how good your equipment is. So we decided to concentrate a little bit on the 30 micrometer lines with the 30 micrometer spacing, just because these are the most, let's say, difficult to print. We saw today that it's actually state of the art to print 30 micron lines, but it's still not as easy as it sounds. You don't just put it inside the machine and and print 30 lines without having all the variables working together. And yeah, also we have to take into consideration the fixation of the substrate. In this case, we were using a porous stone, which is like a porous material which allows the vacuum to fill the whole area. In this case, quite useful because we are using the flexible substrate. Also flexible substrate that look like this. So if you put it over the table, it won't fix anything. You have to push it down a little bit, and then the vacuum, if you have the vacuum in the whole area, it will stay that way. If you will have only points of vacuum, probably it won't work that good. So this is the kind of layout that we printed. So we printed some 30 micron lines with different spacing, so 30 micron spacing, 50 microns, and 100 microns. Also printed the same 50 micron lines with 50 micron spacing and 100 micron lines with 100 micron spacing, and 200 micron lines with 200 micron spacing also. So the layout was exactly like this, so about 100 times 100. And the mesh, if you want to inspect it afterwards, we have one sample over there. So after the presentation, you can take a look at it. So also important, as all my colleagues said already, are the squeegees. In this case, we didn't want to use a lot of squeegees, also because we didn't have too much time. So we decided to use, for this trial, a RKS squeegee, quite hard squeegee, to make sure that we are not spreading the ink too much, that there is not too much bleeding. And also with some paste deflectors, so the paste doesn't go out of the way when printing. So this is also quite useful if you want to scale your process. I think you all know, if you have been doing screen printing for a while, after printing, there's usually, because the paste is rolling, there's usually a small leakage of the paste on the sides, which after maybe 100 prints, you have maybe like 2 lakes of ink on the side that you have to take back to be able to reuse it. So in this case, we use some paste deflectors, which keep the ink together. Of course, not 100%, but quite well that you can use it longer without having to add more paste or to readjust the paste in the process. So as you can see, here's the mesh that we were using. Well, as you can see, I hope you can see it at least. But well, here's the measurements. So we wanted to print 30 micron lines. So we actually, in our layout, we had the 30 micron lines developed on the screen. And as you can see, the result was quite well. So 29, 60, 90 microns on the space. And on the line width, so the emulsion was pretty well done. Sadly, we didn't have any clean room in our lab, so you can see there are small particles of dust or hair, things like that on the area, which may also cause that your lines are not printed all the way, but they have interruptions or they have some short, and yeah. Then the different substrates that we used will be the ceramic, the Kapton, the LTCC green tape, and the solar wafer, and also a few more, also PET. What we wanted to show with this is, of course, you have the, as we saw, a screen that it's quite well done, a mesh that it's wonderful, then top machine, and then just by changing the substrate, the difference in the result at the end is massive. The best result actually that we got was on the LTCC green tapes. We printed with, actually the silver ink that we used is also done for this kind of application. We changed it up also with some inks that were made for flexible substrate. They worked, but in the flexible substrate you get a little bit more bleeding, so the 30 micron lines with the 30 micron spacing was a little bit too small for it. But maybe we will see today. Yesterday we were conducting some trials with the guys here at AIMPLAS, and we saw also when we change it from the PET to the treated PET, the results are massively better. I think on the next presentation maybe we will see something from that. And yeah, well, here you cannot see too much of the results, but hopefully a little bit. So you can see the LTCC is, the lines are quite well. You see the gap between them. When you move to the solar wafer or to the PET, they start to get wobbly. So this is probably due to the surface tension of the different materials. And what we want you to learn from this is that you need this compatibility of the materials to each other. So here you can see the results on the LTCC. So we got really, from a 30 micron line, we really got 30 microns printed. So we didn't have any bleeding at all. And here are the parameters that we use for this this time. So the squeegee, as we said before, is the RKS Carbon 80 Shore. So the printing speed and float was 50 millimeters per second, which is, depending on what you're printing, quite low. Printing pressure was about 80 microns, and the snap off of 1.5. So yeah, so the conclusion is, with screen printing, you have a lot of flexibility on what you can do. You can see here you have flexible substrates, you have rigid substrates, you have scalability, you can have low viscosity inks, high viscosity inks, bigger particles, smaller particles. So it has a lot of flexibility, but you have to know how to use it. You have to know how to use the tools that you are giving, and for that I think the networking today is quite useful. So you can talk to each other. I think no one will have a problem to give some advice to one another. Yeah. So you have the matching of the materials, which is very important, and the flexibility. We say that the screen printing, of course, is flexible, but of course, if you scale it up, you will start losing this flexibility. So if you want to concentrate on one product, you will achieve faster cycle times, very good quality, but at the end, you have to adjust all your machines to specifically that product. So this is something that you have to take into consideration when you are going to scale up your printing. And yeah, so we want to thank Asada for giving us the opportunity to be here today, and also AIMPLAS. We will also like to thank Köhne, which they did the screens for us for the small presentation. And yeah, thank you very much to everybody for being here.
Well, it's been nice to see, the collaboration with ECRA, testing different substrates and also advanced screens. I want to thank Koenen for the collaboration, because I was shipping to them very quickly a sample, and they made it into a very nice screen. And the result of the work in ECRA made possible these interesting conclusions. So I would like to have a round of questions, if any. We are a little bit, behind schedule, like 4 minutes, but I think we can cope with that. Any questions for our colleagues from ECRA? Yep.
Repeated prints. What is the positioning accuracy of your machines?
Positioning is
The repeatability.
okay.
Yeah, he's referring to the degree of accuracy you can achieve with your aligning system.
I know by heart of those for stencil, which is plus minus 20 or 25 microns. But
It will be, I think, 10 to 12 microns by 6 sigma, I think.
Okay.
But it will depend, of course, on the type of machine.
Yeah.
Yeah, I can show you afterwards the different machine with the different accuracy that you will have. Of course, the accuracy won't only be reached by the machine, but also when you use a snap-off, you get also a stretching of the mesh. So every tolerance will add up to the end product. Also, if you are using the flexible substrate, which often go into the oven, they have a small shrinkage, so you will have to add the tolerance to it. So we do not say about the accuracy, but the repeatability of the machine. So every time that you measure the same fiducials, the machine will adjust to the same point. And afterwards, I can show you a few of the machines with the different range of alignment accuracy.
Thank you very much.
Personally, I think is very interesting the point that the way the scalability on the production is achieved, that need to be accompanied with the right materials. So also, from Salamesh, we have been working on, and you will see also in the afternoon, we've been adjusting the meshes, the production of meshes to high resolution, but then we also care for higher tension resistance, basically to ensure long runs. So it's important to select the mesh product for, as well as the screen and everything, and squeegees, for the type of job you want to attempt. Yeah. Okay. Is there any more questions for our colleagues of ECRA? No? Okay. Then maybe we can move to the last presentation. So if Aaron Cabrera from Mateprints comes to the stage, we will adjust the computer quickly.
Well, thank you, Pedro, Azada, AIMPLAS, and the cluster for inviting me to this talk. And also I want to thank NITEC, and especially Raquel, Lisandro, and Sayoa for helping us with the printing of that I go to show you in this presentation. I go to speak a little bit some improvement that we are made with the inks in Mateprints. So I go to speak briefly. Don't worry about the company. Why to use fine line, the needs for fine line, the improvement that we have made, and after I go to speak some concluding remarks, some thoughts that we have thinking this kind of. Okay, thank you. So the company MatePrints is a spin-off of NITEC, that is a technological center devoted to printed electronics and automotive and mechatronics. And now we are a small company that have different kind of investors, public and private. We are members of Platform 3 Neo, and we are part of the board director of Functional Print Cluster. And we design, we manufacturing, and we sales different kind of things. So this you can see a little bit of our timeline from the 2017 when we started the company, and the mass it was step by step going up, and now we have a research and development department, and we have some new. Sorry, it's better from this side. Some new, more new development like silver ink for screen printing, and insulator ink, and so on. So we have inks for screen printing. We have different kind of inks, silver and silver copper inks. We have carbon inks, and also we have special inks for sensors, for electrochemical sensor. And the next development that we are working on is in an insulator, carbon stretchable or immold inks that needs for filing for the last step. And we are just released the SCAG006, that is an ink thinker for membrane keyboard for the people that need to make a curing at low temperatures, maybe 80 degrees, 90 degrees or so. So we have also inkjet inks. We have copper, ATO transparent inks and insulators also. And we hope that at the end of this year we are going to have also a silver ink. And we have offset ink. Up to our knowledge, it's the only offset conductive ink that is in the market right now. We don't know how much. We are very proud of this development. Have been used in the sorry, here. Okay. In a project called Paperonics, as different technological centers like Fraunhofer and others have been used it for make some different kind of things printed. So and in this year was awarded that was of the most innovative development in Spain. Oh, and at the end we have also slow coating inks. Well, in this kind of inks are two inks that can be used for slow coating, have a very low viscosity, and can be used also for rotogravure, flexography, and it has been tested also for sprite printing. Well, MatePrint is different. We have highly competitive in price and condition. We deliver the inks in less than 2 weeks. You can ask for small quantities, and we can tune in our inks depending on your needs. And we have high availability to develop new products if you need it. So, why to use fine line? For us, I think that there are two main fields that is now using fine line. Maybe we can discuss after in the question turn if you know more field that can be used. But I think that the first one is backlighted panels. When you have a panel, you want to backlight it, and you don't want that nobody see the tracks. So you have two possibilities: to use a transparent ink. The problem of this is that sometimes you don't have enough conductivity, or you can use a fine line. So nobody is going to see it. There's another field that is interdigitated electrodes. that requires usually a fine line. For example, the thing that is working Nicola and BCM, and that can be used for different kind of sensor or for transistor or whatever. But I think that the most important use of the fine line is the finger front contact for solar panels, where you need to be as small as possible for avoid the shouting, avoid the problems of losing electricity when you make a line that is so big. So, what do you need for a good fine line printing? For sure, a screen. If you don't have a screen that enough resolution that is going to work well, you are going to have a problem. Also, the printing machine. We just see this ECRA. For me, the most important thing in the printing machine is the reproducibility. You need to. It's difficult to set up the condition for printing for a product. So it's necessary that at the same time that you are going to do the printing is going to be the same. So the reproducibility for me is the most important parameter. The ink, for sure, if you don't have a good ink, you are going to have a problem. Also, substrate, we see that in different substrate, different kind of substrate is going to have different kind of resolution and results. And also, you need to invest in people because it's a very specialized technological development, and you need people with the right formation for that. I go to present here some works that are made on the project that is called Tetroflex. It's a ManuNet call from the European Union and supported also for the regional government of Navarra. We have some partners in Romania. They are trying to make an atmospheric plasma treatment machine for the substrate and get a better printability and resolution. They are getting very good results. Probably we are going to present it in LOPEC. And here I go to speak about the result that we make with the development of the modification of the inks. So, when we start this project, we want to use it for know how the effect of the particles on the substrate affects to the printability and to the resolution of the fine line. So ASADA gives us the opportunity to try with this nice demonstration screen that is 730 threads. And we want to see how this kind of two substrates, a regular PAT and with one specialized PAT that is alpha trace from Chromaline, how it does affect to the printing. And also we have three different inks. Our regular ink for fine line that is 004, that is silver, and also have copper, is trying to make a fine line but with less price than the normal all silver. The 004 plus that is silver. And we want to see what happens if we can change the particles and use this super plus that is also silver. Is not nanometric but is submicrometric. Why submicrometric and not nanometric? Because nanometric are more expensive than submicrometric. So that's the reason. And we want to learn how to change the particles without affect the printability. Because if we learn how to do it, after it's going to be easier to change the particles if we need. So look, I go to show you the results for the three different things. This is for the 004. You need to see here. I go to speak only about this part of here, that is 30 micron lines. So you could see that we get 32 and 50, and so it's more or less or practically the same that you have in the screen. With the fresh trace, when you go to the PAT, is a little bit worse because you have more split, but also we have nice printing. With the 00 P, we get exactly the same. So we can change the particles without affecting to the printability because the results are quite similar. And in case of the SP, we got it exactly the same. So we see the difference between the regular PAT and the flex trace, and we learn how to change the particle without affecting the printability. So, but the printability is not only the important thing. The only important thing in the conductive ink is also the conductivity. So we see we could test it, and we see that you could see here the conductivity of the ink. And we realize of interesting effect is not the same. As you see here, when we measure the resistivity in a millimetric size feature, we have not so much difference in resistivity, but when we go to micrometrics, it's changed really a lot. This is, I think, that is because the behavior of the particle within the ink when it's started to be printed in these small, very small features. Well, this is the same than the last, but only taking one track of 150 microns width and 80 millimeter long. You see that here there's not so much difference, but the thing is maybe a 30%, but after you have 7 times more resistivity. So why we wanted the SP? Because we think that with the 4 and the 4P we cover more or less the features and the size that is more or less using right now in the market, and the SP we are thinking in the future. But we have another, in NITEC we have another screen from other project where we have a 25 micron and 25 gap between it. This is very small things of here. So we could, using flex trace, it was possible to print it. We practically know the difference between the expected size and the real size. And we have also conductivity. So, but if you remember here, we have the problem of the split in the normal PAT, and we think, well, we're trying to modify also some conditions, some solvents and things in the ink to try to get a better result than this. We have here 60 microns, and here, sorry, because this is not the last version. Well, this is half 45 microns. So we improve really a lot, because instead to get 60, we have 45 microns. So, concluding remarks. We have a line. Okay, we have an info-file line that is okay. It's not as well as conductive like the P that is all silver. We have the 004P that is more conductive. Use a dedicated substrate is useful, but it's true that sometimes you cannot use a specialized substrate for your product. Sometimes you need to use a substrate because it must to be that. So we have improving our inks for have a better behavior in other kind of substrate. Use a high resolution script is mandatory. I have these two different pictures. Here is a screen, polyester screen with 100 microns, and the other, when NITEC have the very, very, very busy every time, and we need to speed up the project, so I say, okay, give me the screen. I go to pick it by hand just for make some tests, and I get the screen with one hand and the squeegee with the other, and even doing that, I get a very nice screen, very nice printing. So if you have a very nice ink, for sure, And a good screen you can do if even manually you are going to have very good results. And you see the difference for printing 100 microns with two kind of screen. So it's possible to print at least 25 micron with good conductivity, unless in our condition with using the flex trace. It's true that when we use the PAT and we have some contacts, but we want in the future to don't have it, even using regular PAT. I think that there's not limitation to go further do the measure of the ink. I think that in the market, even if we are not using matte inks, I think that we can go to even to 10 microns. And with good reproducibility also. But I think that probably the limitation is going to be the conductivity of silver. Once you are going less and less fine the line, you are going to have higher and higher and higher resistivity. And even if it were a solid wire of silver, you are going to have a problem because maybe it's not enough conductivity for the use that you want to do. So maybe we are going to reach one day a physical problem over there. I think that maybe it's a thing that is good to discuss about it. Which one is the best ink? I think that there's not the best ink. It's going to depend on what's your goal in your product. If you prefer conductivity, if you prefer price, if you prefer to have a nice and reproducible line, etc. So it's a matter of try and to make a lot of work to get to the good results. Also, thank you to all.
Okay. CHP004. What is the particle size of this?
The particle size is micrometric, but it's low. It's around 2 micrometers or something like that. It's more or less like this. And the SP is not nanometric. It's more than 100 nanometers, but it's less than 1 micrometer. So it's like that.
These are more flakes, or
it's a mix. I was speaking before with we have in matrix we have more than 20 different silver particles tested, and in some inks we use 3 different particles because the particle gives it's a work. It's a completely huge work, and then where the different kind of particle can give you different kind of properties to the ink, and it's so difficult. We are working a lot with that, and we are very happy because we are getting good results.
Okay. A question from Professor.
First, what kind of material do you think would be better than silver?
No, there's no silver. It is the most conductive.
There is no material available unless you think about superconductivity.
Yes, yes, but I was pointing that maybe we need to start to think that there is going to be a physical limitation to the technique at the end. Not because the mesh or not because the inks, but because of the nature of the silver.
The other question, I may have missed it. What was the layer thicknesses of the prints you had when you did the comparison of the three inks? Because the conductivity depends not on the width, it depends on the cross-section of the...
Yeah. Yes, yes, it's around 2 microns.
2 microns?
When it's...
Are you really sure? 2 microns with screen printing?
Yes.
Silver ink?
Well, we can measure again, but...
I was measuring it. I got 2 microns.
You got 2 microns also. Thank you. Because I started to say, well, maybe we measure badly, but yes, it's... yes, I think that this 733, it's so fine, fine. So it's not so much the position.
How much opening it was?
The nominal opening in the screen, it was 30 microns, I think, in here.
Okay.
And then he also tested with another screen that Nitec had.
Yes.
His opening is up to 25 microns.
Yeah.
An EOM of 10 microns. How much was the silver content in your inks? The solid content?
It's around 60%. I'm not sure at all, but it's 60 something. You can also get better or more, but you start to have a so viscous is. If you touch one thing, forget better the conductivity. After you have other problems also.
Watch out, because Professor Hoffner is making a calculation of theoretical ink volume.
Yeah.
Just to add something to your comment of a limit of a conductivity of silver, as Professor Hubner says, I mean, there is a way, and actually the photovoltaic industry have gone around that with, printing multiple layers on top, Yes. So basically you increase the aspect ratio.
Aspect ratio.
Yes, but then after you need to have yes, and then alignment. Thank you. Very, very good, because if you are going to, I don't know, less than 10 microns, the alignment is going to be another problem after.
And then we need to press.
Yes. You need to press one to other.
Yeah.
But, I mean, we will do it in a friendly manner, over dinner and so on.
I think I'm pretty sure that ASUS can deliver that, but you cannot afford it.
The same as the ink, right? You can make in nanoparticles, then it costs more.
Yes, it's true.
Yeah, I mean, little by little, I mean, it's also, the price of a mesh is being stratospheric sometimes, I know. But once we enter into industrial production, the price can lower down. So it's a matter of how the industry adopts these advancements and bring down the overall costs of pieces.
And never the cutting-edge technology is expensive.
Yeah.
After it's converting in a commodity, but at the start it's ever expensive.
Yeah. Okay, is there any more questions for Aaron today? Okay, so it's kind of lunchtime. We have a catering downstairs, so we have to go down the stairs or the elevator, and just outside is being placed, a nice lunch catering, so we can remove the masks and continue our active networking. So we will be back after about 1 hour to organize the groups to go into the live demonstrations that will be performed in the afternoon. I mean, from 2:15, and we will all have the chance to, understand better, the facilities and the equipment available here at the AIMPLAS Research Center. So thank you very much for your attention today, and please keep networking for the rest of the day and even the night for some of us.